Once again, part 2, and it is a topic mathematical method of the physics. So let's deal with the first topic, green functions. The green functions solve the linear differential equation representing response point delta functions and turning the PD into the integral over the sources and boundaries. Now operator L and green function G R comma R dash satisfy that L and G R comma R dash equal to delta bracket 1 R minus R dash appropriate boundary condition solution L U bracket 1 R equal to FR convolution U R equal to the integral G R comma R dash and f r dash dr dash plus boundary terms. Key example Poisson's equations Laplace square phi equal to the minus f3 space Green's functions g r comma r dash equal to the 1 by the 4 pi mod r minus r dash the Coulomb potential solution phi r equal to the 1 by 4 pi integral f r dash divided by the mod r minus r dash dr. Helmholtz equation bracket 1 Laplace square plus k square mu equal to the minus f and g equal to the e की power I k mod r minus r dash divided by 4 pi and mod of the r minus r dash outgoing waves. 1D harmonic oscillators d square u by dx square and plus w square u equal to a piecewise linear and g equal to the x comma x dash. Derivation by the Green's identity for the L equal to the Laplace square Green's second identity equal to the integral bracket 1 u into the Laplace square v and minus v into the Laplace square u and dv equal to the closed integral bracket 1 u d and v minus v d and u and bracket 1 ds, where the v equal to the g and Laplace square g equal to the minus delta yields integral solution directly separating volume source integral from the boundary contribution. Properties and applications symmetry g bracket 1 r comma r dash equal to the g bracket 1 r dash comma r for the self adjoint operators boundary conditions. Now Dirichlet. Dirichlet's G equal to the 0, Newman delta G and by the del n equal to the 0 or the Robbins and method of images constructed the G for the simple domain by reflecting the sources. Time domain retarded or advanced green function for the wave equation solve the causality used throughout physics, electrostatics, heat conductions, quantum scattering, vibration analysis. Now partial differential equation, Laplace wave and heat equation 2 and 3 dimension. Partial differential equations like the Laplace wave and heat governed steady state propagations, diffusion phenomena 2D, 3D solved by the separation of variables into the products unvariate and functions. Laplace equation Laplace square phi equal to the 0 steady charge and free electrostatic in a 2D Cartesian rectangle assume phi x comma y equal to the x x and y y and yielding the x double dash by x equal to the minus y double dash by the y equal to k square solution sin kx sin hky exponential 3D spherical phi bracket 1 r comma theta equal to the r r and theta theta phi phi radial r की power l and r की power l then divide by r की power l plus 1 angular Legendre and spherical harmonics and pl की power m cos theta e की power I m phi and boundary condition determines coefficient Fourier series wave equations Laplace square u equal to the c की power minus 2 del t की power 2 u vibration em waves 2D polar separation gives the Bessel function j m bracket 1 k r for the radial and the cos bracket 1 m phi minus wt angular temporal and the 3D spherical waves u bracket 1 r comma t and equal to 1 by r and f r minus ct. So are the plane waves e I bracket 1 k r minus omega t with the omega equal to ck and the D'Alembert or Fourier's method for initial boundary value problems. Now heat equations Laplace square t equal to alpha minus 1 delta t t diffusion 2D rectangle separation sine bracket 1 m pi x by the Lx sine n pi y by the Ly e की power minus bracket 1 m square pi square by the Lx square plus n square pi square by the Ly square alpha t Fourier series initial t x y 0 3D similar exponential decay fastest high modes steady state reduces Laplace. Now equation physics and separations yields and 2D 3D special functions Laplace 3D field science hyperspherical harmonics Legendre Bessel cylindrical wave propagations oscillatory Bessel plane waves and Hankel outgoing and heat diffusion exponential transient error function 1D exact. Now let's solve the 3D Laplace equation in the spherical coordinates with the boundary data. 3D Laplace equation Laplace square phi equal to the 0 spherical coordinates r theta phi and solved by separation variables yielding general solution series radial powers times spherical harmonics matching boundary data spherical surface. Separation variables assume the phi r theta phi and r and theta theta and phi phi. Laplacian spherical coordinates separates into the ordinary differential equations r square r double dash and plus 2 r dash by the r dash minus 1 by theta sine theta d by d theta sine theta d by the d theta by the d theta and minus 1 by theta sine square theta and d square phi by the d phi square equal to L into the L plus 1 yielding the phi double dash plus m square phi equal to the 0 and periodic m equal to the 0 comma 1 associated Legendre equation for the theta and solution PLM cos theta L equal to the mod m and comma mod m plus 1 radial r square r double dash plus 2 r dash minus L bracket 1 L plus 1 and r. So equal to 0 power r equal to the a r की power L plus b r की power minus L minus 1 interior solution bracket 1 r less than a take r की power L and regular at the origin exterior take r की power minus L minus 1 vanishing at infinity general solution with the boundary data on a sphere r equal to a phi bracket 1 a theta phi equal to f theta phi expand in the orthonormal spherical harmonics yl की power yl m theta phi f bracket 1 theta comma phi summation L equal to 0 infinity summation m equal to minus L e की CLM YLM theta phi CLM equal to integral YLM star FD omega interior solution phi r theta phi and summation L equal to 0 infinity m equal to the m equal to the minus L to the L, CLM and bracket 1 R by A and L and YLM theta comma phi. So further exterior replace the R divided by A की power L by the A divided by the R की power L plus 1. Now example azimuthal symmetry if the f theta no phi dependence m equal to 0 phi equal to the phi bracket 1 r theta and summation infinity L equal to the 0 al by the r by alpha L and pl cos theta with the al equal to the 2l plus 1 by 2 integral 0 to the pi and f theta pl cos theta sin theta d theta matches the boundary exactly. Now, further, next topic will be the elements of the computational technique, roots of functions, interpolations, extrapolation, integration by trapezoid, Simpson's rule, computational techniques approximate solution to the functions, roots, finding, locates the zeros, interpolation, extrapolation, estimate the values, and by the between the beyond data and trapezoidal Simpson's rules numerically integrate. So root finding. So bisection bracket root in angular bracket a comma b bracket 1 f a into f b less than 0, midpoint c equal to the a plus b divided by 2, half interval linear convergence. Now neutral reflection xn plus 1 equal to xn minus fxn by the f dash xn quadratic if the near root and needs derivative and starting guess. Second xn plus 1 equal to xn minus fxn divide fxn bracket 1 xn minus xn minus 1 divide by the fxn minus 1 bracket 1 number of the derivatives, no derivative, interpolation and extrapolation. Lagrange's for the points xi, yi, px equal to summation yi pi j not equal to I x minus xj by the xi minus xj exact at the nodes. Runge oscillation, high order Newton divided the difference and hierarchical polynomials linear y equal to the y naught plus y1 minus y naught bracket 1 x minus x naught divided by the x1 minus x naught. Extrapolation extends beyond data, less accurate and a higher error. Numerical integrations. Now the trapezoidal rule. So integral a to the b f j f a x dx equal to the h by 2 bracket 1 f a plus 2 summation f x I plus f b comma h equal to the b minus a divided by n either order h की power of the 2 composite for the n interval. Simpson's rule parabolic integral a to the b integral a to the b f equal to the h divide by the 3 bracket 1 f a plus 4 f a plus 4 summation f x odd. So for summation fx odd plus 2 into summation plus 2 into summation fx even plus fb comma even n bracket 1 even n bracket 1 error order h की power for superior for the smooth functions. Now error comparison method order use case trapezoidal order h की power 2 quick low accuracy Simpsons order h की power 4 and smooth integrants Newton quadratic differentiable good case bisection linear bracketed robust. Now, next will be the Rangikutta method and solve first order ODE y dash ft comma y t naught y naught by the higher order Taylor approximation without the derivatives with the RK4 standard fourth order method classical RK4 method forum t and yn step size h k1 equal to the f t n comma yn k2 equal to f t n plus h by 2 comma yn plus h k1 divided by the 2 k3 equal to the f bracket 1 tn h by 2 comma yn plus h k2 by the 2 bracket 1 comma k4 f bracket 1 tn plus h plus yn into the hk3 and therefore the yn plus 1 equal to the yn plus h divided by the 6 bracket 1 k1 plus 2k2 plus 2k3 plus k4 comma and tn plus 1 equal to tn plus h. Location truncation error order h की power 5 global order h की power 4. Local truncation error will be the order h to power 5 and global order h to power 4. So system equation y dash equal to the ft comma y, apply the component wise example, y dash equal to the minus y and y0 equal to the 1, exact y equal to the e to power minus t, wrong equal to 4 with h equal to zero point 0.1. First step, k1 equal to the minus 1, K2 equal to the minus 0.995, K3 equal to the minus 0.995, K4 equal to the minus 0.990, Y1 equal to the 0.9048, exact 0.9048. Now comparison of the RK methods, method, order, slopes, evaluated stability. Euler 1 1 poor, RK2 RK2 2 2 fair, RK4 RK4 4 4 good. Now next topic will be the what? Let deal with the finite difference methods and tensors. Finite difference method approximate PDE derivatives on the grids, replacing du by dx and ui plus 1 minus ui divided by the h for the numerical solution. Tensors enable the low rank approximate for the high dimensional PDE in the finite difference schemes, reducing the computational caused by the formats like the tensor train TT. Now finite difference approximation, forward ui plus 1 minus ui divided by the h, backward ui minus ui minus 1 by the h. Central will be the ui plus 1 minus ui minus 1 by the 2h, and the second order accurate. For the 2D Laplace square u and equal to the 0, 5-point stencils, and uij equal to the 1 by 4 ui plus 1 and ui plus 1, ui plus 1 comma j plus ui minus 1 comma j, and ui 1 by u I is equal to the 1 by 4 bracket 1 u I plus 1 comma j plus u I minus 1 and the j plus u I j plus 1 plus u I j minus 1 leads to the sparse linear system solved iteratively and Gauss-Seidel. Application to the PDE. Now time dependent heat explicit Uijn plus 1 equal to Uijn and plus alpha delta T and by h square bracket 1 Ui plus 1 comma j n plus minus 4 Uij CFL stability and alpha delta T by h square less than equal to 1 by 2. Now, implicit schemes unconditionally stable by the matrix solves the higher order by the larger tensors. Now, tensors in the finite differences. Multidimensional PDE discretized yield height D tensors, low rank TT decomposes Ux equal to the summation R and G1 X1 GD XD rank X rank RK less than N. Tensor train finite differences apply the operators separately, enabling the order O D and R ki power 2 solves versus order O N ki power D mimetic variants and preserve divergence free properties. Now comparisons. Now expect standard FD tensor enhanced FD dimensionality low to 3D and high low to 3D high 10 plus by low rank cost order n ki power 2 per iter and order DNR power to storage full grid compressed factors. Now let's interesting topic. It is an introduction group theory SU2O3. So SU2 is the special unitary group 2 cross 2 complex matrices determinant 1 acting double cover rotation group SO, 3 bracket 1 3 or order O3 without reflections order 3. Order 3 includes the improper rotation reflection determinant equal to the minus 1 while the SU2 parameterizes proper rotation by the quaternions with the 2 is to 1 homomorphism SU2 and tends to SO3. SU2 structure. SU2 structures elements U equal to the AB minus B bar A bar and comma mod A square plus mod B square equal to 1. 3 is sphere topology, Lie algebra SU2 anti-Hermitian matrices generated by the Pauli matrices sigma I divided by the 2 colon T bracket 1 T I comma T J and equal to the I zeta I J K T K isomorphic to the SO3 irreducible representation spin J dimension 2J plus 1 O3 relations O3 equal to the SO3 union reflection SO3 uh, congruent to the SU2 by plus minus L antipodal identification on the S3 homomorphism U tends to the RU where V dot sigma tend to the U V dot sigma U for the covers the covers the angular momentum in the quantum mechanics SU2 for the half integers. Representations, comparisons, group dimensions, topology, physics rule. SU2 3 manifold, 3 s power 3 simply connected, spin, weak force, SO3 3 RP3 RP3 double cover needed rotations order O3 3 edits parity full orthogonal transformations. Now let's deal with the classical mechanics. Now, the topic was dynamical systems. Dynamical system, model time evaluation, order differential equations, maps, classified continuous x dot equal to fx or discrete xn plus 1 equal to fxn. Analysis focuses fixed point stability, bifurcation, chaos with the tools like linearizations, Lyapunov, and exponents. Now fix the points and stability equilibria solve fx star equal to the 0 and Jacobian dfx star eigenvalue determine type hyperbolic sink and r lambda less than 0 source greater than the 0 saddle mixed and center pure imaginary phase portraits visualize the flow bifurcations are the bifurcation parameter dependent saddle node new equilibria collide transcritical exchange stability pitchfork symmetry breaking branches hopf limit cycle birth by the eigenvalue crossing the imaginary axis detect by the normal forms example x dot equal to the r x minus x cube supercritical pitchfork chaos and strange attractors nonlinear system exhibit sensitive dependence Lorentz equation x dot equal to the sigma bracket 1 y minus x comma y dot equal to the x bracket 1 rho minus z minus y z dot equal to the xy minus beta z bracket 1 row minus 28 yield a butterfly attractor. Now positive Lyapunov exponent lambda greater than the 0 logistic map xn plus 1 equal to the x r x n bracket 1 minus xn. Period doubles chaos r 3.57 method comparisons. Now the type example equation key feature linear x dot equal to the ax exponential solutions nonlinear van der Pol x double dot minus mu bracket 1 minus x square x dot plus x equal to the 0 limit cycle chaotic is the Laurent and fractal basin. And next topic will be the phase space dynamic. Phase space dynamics. Phase space dynamic. Phase space phase space dynamics visualize trajectories of the dynamical system in the space of all the state variables revealing the attractors repellers and the basins for the continuous x dot equal to the fx or the discrete system. Phase portrait for the 2D autonomous x dot equal to the p bracket 1 x comma y and y dot equal to the q x comma y. Plot the vector field v equal to the p comma k streamlines integral curves fixed points classified and by the trace determinant Jacobian nodes and real eigenvalues spiral complex and settles opposite the signs and example damped pendulum spiral to the origins undamped orbit ellipses higher dimensions and attractors 3D phase space for the Lorentz trajectory converse butterflies shaped and the strange attractor fractal positive Lyapunov exponents limit the cycles and periodic orbits bound by the Poincare and the Bendixson and Theorem 2D Hamiltonian system conserve volume, Liouville, and the phase space incompressible and Poincare sections sin slice Heidi phase space now the hypersurface transversal to the flow and yielding return map p summation to summation detects the tori quasi-periodic chaos, strange attractors, logistic map phase plot and show the period, double cascade counter set. Now key concept, feature, signature, and phase space example system. Fixed point, intersections, and x equal to the minus x and sync. Limit cycle, closed loop, Van der Pol, chaos, dense, non-repeating, and Lorentz butterfly manifold invariant curves surfaces stable unstable for the saddles. Then further topic will be the stability analysis. Stability analysis determines if the fixed points or trajectories of the trajectories of the dynamical system remain near the perturbation over the time using the linearization or the Lyapunov functions. Linearization bracket 1 indirect method for x dot equal to the fx equilibrium f bracket 1 x star equal to the 0 Jacobian a equal to the d f x star asymptotically stable if all the r bracket one lambda I less than 0 sync, and unstable if any r bracket one lambda I and greater than 0 source or stable. Now hyperbolic. If the no zero imaginary parts linearizes and the nonlinear behavior locally, Lyapunov direct method construct the positive definite and Vx is greater than the zero and V0 equal to the zero radially unbound if the V dot equal to the Laplace V and dot F and less than equal to the zero stable v less than the zero negative definite asymptotically stable for the linear x dot equal to the ax and solve the Lyapunov equation a to power t and the p plus pa equal to the minus q and bracket 1p greater than 0 q greater than 0 La Salle invariance added the attractors. Now the types of stability Lyapunov stable perturbation stay bounded nearby asymptotic now converge to equilibrium exponential mod xt less than equal to the k bar mod x naught e to power minus alpha t. Method comparison, the method requirement conclusion strength, linearization, Jacobian eigenvalues, local hyperbolic, Lyapunov, energy like v dot, global possible, frequency, next body, and linear system only. Our next topic will be Poisson's bracket canonical transformations. So Poisson bracket define simple lactic structure Hamiltonian mechanics generating time evolution symmetrics by the angular bracket f comma h equal to summation I bracket 1 df by the dq I dh and by dpi minus df by the dpi by dh and by dqi. So properties and the Hamiltonian equation antisymmetric bracket 1 f comma g equal to the minus bracket 1 g comma f. So bilinear Lebanese bracket 1 f g comma h. So equal to f bracket 1 g comma h plus f comma h and bracket 1 g Jacobi identity fundamental bracket 1 qi pj equal to the delta ij bracket 1 qi equal to the bracket 1 pij and equal to bracket 1 pipj equal to 0 yields qi dot equal to the bracket 1 qi comma h. So equal to the delta h by dpi and pi dot equal to bracket 1 pi h and equal to the minus delta h by the q delta qi del qi conserved quantities satisfy bracket 1 f comma h equal to the 0. Now canonical transformation map bracket 1 q comma p and q comma p preserving the Poisson bracket q I q j and equal to bracket 1 p I comma p j and equal to the 0 and bracket 1 q I p j equal to delta I j. So generated by the type 1 f bracket 1 q comma q and pi equal to df df divided by dqi. So pj equal to the minus df by the dqj and type 2 f q comma p etc. New Hamiltonian k bracket 1 q comma p equal to h bracket 1 q and bracket 1 q comma p bracket 1 q comma p. So plus df by dt and point transformation identity on the p or canonical application action angle variables transforms to the ji I phi j equal to delta ij and comma h equal to the ha symmetries by the noether and dqi and zeta and qig quantum analog commutators q cap p cap ih cap replace qp equal to the 1 transformation tables type generating functions preserves forms. Now the one fqq equal to the pdq plus pdq. So two fqp now pdq minus q dp identity will be the F equal to the QQ and rotations. Now, hi. And now next topic will be the symmetry invariance. Symmetry invariance no ethers theorem. No ethers theorem links the continuous symmetries of the system action or Lagrangian to conserve quantities fundamental in the physics for explaining conservation laws like energy momentum. Symmetry and invariance. A symmetry is a transformation time shift t tends to the t plus zeta. Space translation. Space translation x tends to the x plus a, leaving the Lagrangian L bracket 1 q comma q dash unchanged up to the total time derivative delta L equal to df by dt. Invariance means physics laws identical under such changes. System itself need not be symmetric. Asymmetric asteroid conserves the angular momentum. No ether theorem statement for Lagrangian L symmetry variation dqi equal to the eta ki bracket 1 q comma t conserve current q equal to the summation pi ki minus f with the dq by the dt on the cell and Euler Lagrange satisfied. Derivation d by dt summation dl by dqi dot by and dot into dqi minus f equal to dl by dqi and dot into dqi equal to 0. By the symmetry and equation of the motion, key examples time translation delta L equal to the 0, energy H minus energy H equal to summation PIQI dot minus L conserved, space translations. Now momentum P conserved, rotation angular momentum L equal to the Q cross P, and symmetries and the laws. Symmetry and conserved quantity, time translations, energy, space translations, linear momentum, rotation, angular momentum, U1 Gauss chart. Now, next topic will be Hamilton and Jacobi theory. Hamilton-Jacobi theory reformulates Hamilton-Jacobi reformulates Hamiltonian mechanics by the canonical transformation generated by the principal functions S bracket 1 q comma t, reducing the reducing the motion to constants through the Hamilton-Jacobi equation HJE solution yield the action angle variable for the integrable system. Hamilton-Jacobi equation for the Hamiltonian H bracket 1 QPT seek the type 2 and generating the function S bracket 1 QPT such that the new K bracket 1 QPT equal to the 0. Therefore, ds by the dt plus h bracket 1 q comma ds by the dq comma t equal to the 0. Semicolon pi equal to the ds divided by dqi comma qj d equal to the ds divided by the dpj. Time independent separate s equal to the w bracket 1 q comma alpha minus et bracket 1 e constant h comma hje becomes h bracket 1 h bracket 1 q delta w q comma delta w comma e equal to the e. Cyclic coordinates simplify the w quadrature qi equal to the qi bracket 1 alpha comma t. So action angle variables integrable transform to the J action, comma closed integral PDQ angles W linear in the time. HJE HJE separates completely H equal to Hj and W dot K. W dot K equal to Dh by the del Jk. So equal to Wkj and Jk cap equal to 0 frequencies omega k resonance if rotationally related application will be the Kepler problem W equal to the minus u divided by the 2 root 2 e integral dr divided by the under root r की power minus 1 minus l की power 2 minus l की power 2 divided by the 2 mu r की power 2 minus e divided by the mu yields the elliptical orbits by the eccentric anomaly. Links to quantum WKB semi-classics S equal to HES. S equal to the HES divided by H and key features, aspect and role in the HJ theory, generating S canonical to the constants, separation, time independent H, and action J adiabatic invariants. So thus the topic of the mathematical methods of physics is over. No, so classical mechanics is over. Now further deal with the electromagnetic theory. Dispersion's relation in the plasma. In a plasma, dispersal relation links wave frequency omega, wave number k, determining wave propagate, how fast they travel. They follow from linearizing the plasma equation, fluid or kinetic plus Maxwell equation, demanding the non-trivial and wave solution, generating the idea for the small perturbations and proportional to the e ki power I bracket 1 k I kx minus omega t. The governing linear equations give a condition d bracket 1 omega comma k equal to the 0. This function d encodes the plasma parameters as the plasma frequency omega p and cyclotron frequency omega c, temperature and propagation angle. Phase and the group velocities follow the Vph equal to the omega upon the k. So Vg equal to the d omega upon the dk. So simple electrostatic Langmuir wave. Now for an unmagnetized cold electron plasma with a fixed ions and a longitudinal electrostatic oscillation gives omega square equal to the omega p square, where the omega p square equal to the n e into the e square divided by the epsilon naught me, including the electron, temperature, Bohm, gross corrections yields omega square equal to the omega p square plus 3k square into the Vth square. So high k wave propagate faster due to the pressure or the thermal effects. Electromagnetic waves in an unmagnetized plasma. Further transverse electromagnetic waves in the cold unmagnetized plasma. The dispersion relation is the omega square equal to the omega p square plus c square k square, and there is a cutoff for the omega less than omega p. No real k exists. So waves are evanescent and cannot propagate. For the omega greater than the omega p, the relations approaches the vacuum. equal to omega equal to the ck, and magnetized plasma. Magnetized plasma qualitative with a background magnetic field B naught. The dispersion relation splits into the multiple branch. Example R by L modes, ordinary, extraordinary modes, alpha band, and magnetosonic wave. General condition again d bracket 1 omega comma k equal to 0, but now depends on the angle between the k and b naught, giving anisotropic propagation and resonance at the omega equal to the n omega c. So omega equal to the n omega c. So if you specify unmagnetized as the magnetized, cold versus warm, electrostatic versus electromagnetic, concrete step by step derivation and specific divergent relation given. So let's derive the plasma dispersion relation from the Balsov equations. Now, derivations of the plasma dispersion relation from the Balsov equation yields longitudinal electrostatic Langmuir wave relation, unmagnetized collision-less plasma incorporating Landau damping by the plasma dispersion function. Balsov equations linearization. Balsov equation is species and yes dfn by dt plus v dot Laplace fs plus qs by the ms bracket 1 e plus v cross b dot vv Laplace v fs equal to the 0, linearize around the equilibrium fs equal to f0 s v and plus f1 srvt and equal to the e1 b equal to b naught and plus b1 equal to 0. Unmagnetized electrostatic E1 equal to the minus Laplace phi 1 plane wave and set is F1 yes phi 1 and proportional to the e की power I kx minus omega t yielding I omega integral F1 yes plus ik Vx F1 yes minus qs by the ms ik phi 1 ik phi 1 df not yes by the dvx my equal to the 0. Solve f1 yes equal to the qs k phi 1 by the ms df not yes by omega minus kvs by the dvx. Poisson equation closer. Density perturbations n1s equal to the integral f1s d3v equal to the minus qs k phi 1 by ms. Now integral df naught s dvx by the omega minus kvx d3 v Poissons and Laplace dot e1 equal to the minus k square phi 1 and equal to the summation yes qs inverse qs n1 s by the epsilon naught. So 1 equal to the summation 1 equal to the summation yes qs square epsilon naught ms k square integral del f naught yes by the dvx divided by the omega minus kvx and d3v Poisson's Laplace dot e1 equal to the minus k square phi 1 equal to the summation yes qs n1 yes divided by epsilon naught. So therefore 1 equal to the summation yes into summation yes qs square divided by the epsilon naught ms k square epsilon naught ms k square and integral df naught yes by the dvx divided by the omega minus kvx d3v equal to the 1 plus summation chi s omega comma k equal to the 0, where the chi s is suspectivity for the 1D Maxwellian electrons and F0e equal to the n0 bracket 1 me divided by the 2 pi t e की power 1 by 2 e की power minus e की power minus m e v e m e v e v x की power 2 divided by the 2 t e. Integral becomes the plasma. Integrals become the plasma dispersion function z eta equal to the 1 by the root pi integral minus infinity to infinity and e की power minus t square dt by the t minus eta. So eta will be the eta equal to the omega by the k root 2 v th and vth equal to the root t e by mc. Dispersion relation electrons plus fixed ions equal to the 1 plus 1 by k square lambda de 1 by 2 z dash eta equal to 0 where the lambda de equal to vth and by the omega p and omega p square equal to n naught e square by epsilon naught me. Large argument expansion z dash omega equal to the minus 2 1 plus 1 by 2 zeta square plus dot dot and colon omega naught and omega p square bracket 1 plus 3k square by lambda d square Bohem gross. Analytical continuation past pole gives the now the omega less than Landau damping. Now next topic will be what? Let me tell. Lorentz invariance of the Maxwell equations. Maxwell equations are the Lorentz invariant, meaning they retain the same form any inertial frame related Lorentz transformations, unlike under the Gaussian transformation. Covariant formulation express the field's antisymmetric tensors. Now the F mu comma V equal to the del U A V minus del V and A U for potential Maxwell del U into the F del U into the F mu V equal to the mu theta Jacobian V homogeneous del lambda F mu V equal to the 0. Bianchi identity for current J mu equal to the rho c comma j both sides transform as the four vectors under the Lorentz boost preserving equation form E comma B mix and parallel perpendicular components interchange roles. Explicit boost derivation x directions velocity v Lorentz t dash equal to lambda bracket 1 t minus vx divided by c square comma x dash equal to the lambda bracket 1 x minus vt y dash equal to the y and x dash z dash equal to the z bracket 1 lambda equal to the 1 divided by the under root 1 minus v square by the c square field transformation ex dash equal to the ex ey dash equal to the lambda bracket 1 ey minus mu and bz and Ez dash equal to lambda bracket 1 Ez plus mu and By and Bx dash equal to the Bx and By dash equal to lambda By and plus V E keep Ez by the C square there, comma Bz dash equal to lambda bracket 1 Bz minus mu V and Ey by the C square. Charge and magnetic densities rho dash equal to the lambda bracket 1 the rho minus Vjx by the c square. Verify the Gauss laws. Original Laplace dot equal to the rho by epsilon naught. Prime frame compute del x dash ex dash plus del y dash ey dash. Now the plus del z dash ez dash equal to lambda bracket 1 del x ex del y ey minus v bz plus del z bracket 1 ez plus v by equal to the lambda Laplace dot e minus v bracket 1 del y and bz minus del z by. So equal to the lambda bracket 1 rho divided by epsilon naught minus v and bracket में Laplace cross the b and x and by the mu naught c square by plus Vjx and by the epsilon naught c square using the Laplace cross the b and mu naught j a plus mu naught epsilon naught and del t e Lauren and rho dash j rho t j dash and equals rho k power rho t and epsilon naught. Similar for the equation in variable tables, the equation transforms to Laplace dot e by equal to rho by epsilon naught, same form. Laplace dot b equal to 0, same form. Laplace cross e equal to minus del t b, same form. Ampere Maxwell, same form. Now further transmissions lines and the waveguides. Our next topic will be the transmission lines and the waveguides. Transmission lines guides the TEM waves between the two conductors. Waveguides confine the higher modes TE or TM in the hollow metal structures for the microwaves, avoiding the losses in the coaxial cables at the high frequency. Transmission lines. Two conductor structure coaxial twin laid microstrip support the TEM mode where E and H fields are transferred to propagation. Telegrapher equation from the Maxwell del V by del Z equal to the minus L del I by dt minus Ri comma di divided by the dz equal to the minus c into dv by the dt minus gv. Harmonic solution yield the propagation constant lambda g this is y and under root r plus j omega l into the g plus j omega c characteristic impedance. Now z not equal to the under root r plus j omega l inductance. So divide by the g plus j omega s low loss and limit gamma equal to the alpha plus j into the beta, comma beta equal to the omega under root LC. So waveguides, single conductor hollow tubes, rectangular, circular, cannot support the TEM no return path and propagate TE or TM modes above the cutoff and FC rectangular width A and the height B. TE minimum cutoff KC equal to the under root m pi divided by the a की power 2 plus n pi divided by the b की power 2. Dispersion omega square divided by the c square equal to the k square plus kc square. Phase velocity vp equal to the c divided by sine theta greater than the c. Group vg equal to the c cos theta less than the c. Dominant te10 equal to the fc c divided by 2a. Mode comparison. Structure, modes, cutoff frequency application, transmissions line TEM, none, RF up to the gigahertz, rectangular waveguide TE upon TM, FC greater than 0, microwave 10s gigahertz, circular TE upon TM varies. Now radar and low loss. Let's derive the cutoff frequency for the rectangular waveguide. Rectangular waveguides support TE-TM modes cutoff frequency below the waves in evanescence. Derive solving Helmholtz equation, boundary condition, conducting walls. Wave equation separation assume the time harmonic fields proportional e की power minus I omega t and propagation e की power I k z z along the guide z direction from the Maxwell derived scalar Helmholtz Laplace square zeta and plus k square zeta equal to the 0. K square equal to the omega square mu epsilon not equal to omega square by the c square. Separate the zeta x comma y comma z equal to the phi bracket 1 x comma y and e to power I k z z yielding the 2D eigenvalue problem. Now Laplace xy square phi plus kc square phi and equal to the 0. K square equal to the kc square plus kz square. Kc is the cutoff. Kc is the cutoff, wave number, and a boundary condition, rectangular guide, 0 less than x less than the a width and 0 less than y less than the b, that is the height, and a is the greater than the b. Perfect conductor, tangential equal to 0 on the walls. Now TE modes Hz base phi equal to the Hz and cos m pi x by the a cos n pi y by the b. Eigenvalues the Kc equal to the under root m pi divided by the a ki power 2 plus n pi divided by the b ki power 2 mn comma 0 comma 1. So further not both 0. Te modes Ez base phi equal to Ez sine bracket 1 m pi x divided by the a sine n pi y divided by the b. Same kc mn 1 2. Cutoff frequency fc equal to the ckc by the 2 pi equal to the c divided by the 2 under root m divided by the a ki power 2 plus n divided by the b ki power 2. Dominant mode TE bracket 110 m equal to the 1 n equal to the 0 fc equal to the c divided by 2a. Lowest for the f greater than the fc. Kz equal to the under root k square minus kc square real and propagating f is less than fc imaginary. F less than fc imaginary. Evanescent mode and cutoff. Now mode fc expression te10 c by 2a te01 c by 2b te11. Now let's the next topic will be what? Radiation from the moving charges. Radiation from the moving charges and dipoles and retarded potentials. Radiation from accelerating charges arises from non-static terms in the Leonard with y chart potential. Dipole radiations dominating for the non-relativistic speeds and localized sources. Now retarded potentials. Scalar vector potential moving charges use the retarded time tr equal to the t minus mod r minus r dash tr divided by the c. Phi bracket 1 r comma t equal to 1 by 4 pi epsilon naught q divided by the 1 minus n into the beta bracket 1 r and tr. So a bracket 1 the r comma t and equal to the mu naught divided by the 4 pi into the q v divided by the 1 minus n into the beta into the r and te, where r equal to the r minus r dash tr. So comma r equal to the r mod of r and beta equal to the v by c. N equal to the r by r and fields from the E equal to the minus Laplace phi and the minus del t a and comma b equal to the Laplace cross a. Fields from the single charge exact Leonard which are fields split velocity near acceleration for terms radiation 1 by r part. Irradiations equal to the mu naught q by the 4 pi r and n cross bracket 1 n minus beta cross beta dot and divided by the 1 minus n beta square and trc and b rad and equal to the 1 by the c n into the e rad. Non-relativistic beta less than the 1 irradiation and mu naught q divided by the 4 pi rc bracket 1 n n cross bracket 1 n cross b double dot and the tr and sine square theta pattern theta angle between the v double dot comma n Larmor formula total power p minus mu naught q divided by 6 pi c. So dipole radiation for the system PT, for system with the PT summation QIRIT for filled multipole expansion. E radiation is equal to the minus mu naught by the 4 pi r n cross bracket 1 n cross p double dot, and the TR and EB radiation equal to the minus 1 by the CR into N into EREZ dot. Power per solid angles dp by the omega equal to the mu naught p double dot square by 32 pi square c sine square theta, total p equal to the mu naught p double dot square by the 12 pi c. Now power pattern, source pattern, total power, single charge sine square theta, Larmor, electric dipole sine square theta, p double dot square, magnetic dipole sine square theta, m double dot square divided by the c की power of the 2. Now thus the electromagnetic theories are finished. Now let's start dealing with the quantum mechanics. Quantum mechanics, and the topic is spin orbit coupling, and the fine structures. Spin orbit coupling, relativistic interactions between the electron spin S and its orbital angular momentum L, and it is the main contributor to the fine structure splitting of the atomic energy level. Conceptually, electrons rest frame moving nucleus creates a magnetic field that interacts with the electron's magnetic moment. Spin orbit Hamiltonian, simplest hydrogenic, non-relativistic plus first relativistic corrections, and picture spin orbit interactions written as the HSO equal to summation R L dot S, where zeta R depends on the radial coordinate on the Z nuclear charge. For the central Coulomb potential, V are equal to the minus Z e की power 2 divided by the 4 pi epsilon naught R. One finds now HSO proportional to the 1 by R into dV by dr L dot S is proportional to the Z upon R cube L dot S, because J equal to the L plus S operator L dot S can be rewritten in the terms of the JLS. L dot S equal to the 1 upon the 2 bracket 1 J square minus L square minus S square. Thus the spin orbit energy shift given N L J is the delta E S O bracket 1 N L J proportional to the 1 upon the 2 angular bracket J bracket 1 J plus 1 minus L bracket 1 L plus 1 minus S bracket 1 S plus 1, with S minus 1 divided by 2 for electron. This shows that levels with the different J split energy even if they share the same N and L. Fine structure of the hydrogen. Fine structure in the hydrogen or hydrogen-like ions comes from the three main corrections to the non-relativistic Bohr-Schrödinger energies. Bohr-Schrödinger energy, relativistic kinetic energy corrections, spin orbit coupling, Darwin term, contact term, relevant yes states. To find the order in the perturbation theory, this can be combined into the single structure corrections. Delta EFS n comma j equal to en0 z alpha की power 2 bracket 1 upon n 3 by 4 minus n by the j plus 1 by the 2. En0 is the non-relativistic energy. Alpha is the fine structure constant. The crucial point is that corrected energy depends on the J, not a L. So the levels like the 2p 1 by 2 and 2p 3 by 2 split. Overall, degeneracies are reduced. Coupling schemes and term symbols: light atoms, Russell Saunders, LS coupling, vector addition, L equal to the summation I and L I and S equal to summation ISI. Then J equal to the L plus S. Term symbols to S plus 1 LJ example to P3 by 2. Spin orbit interactions lifts the degeneration between the J for the given L comma S, giving the fine structure multiplate. The energy on ordering follows sign effective zeta R value J for a typical 1 electron outer shell. Larger J has the slightly lower or the higher energy depending on the details of the potential. If you want, next step can be worked example computing fine structure splitting between the two specific hydrogen levels. An example 2p1 by 2 versus 2p3 by 2 using the perturbation theory. No, for next topic will be what? WKB approximate. WKB approximation. WKB WKB Ventzel Kramers Brillouin approximation provides the semi-classical solution time independent Schrodinger equation slowly varying the potential bridging the quantum and classical mechanics. WKB wave function for the minus h ki power 2 by 2m zeta phi n double dash plus vx phi equal to e phi. Assume the phi x equal to the ax e ki power isx by h. Expand s equal to s naught plus h s1 plus h square s2 leading order s naught dash square equal to p square x equal to the 2m e minus vx. So yes not x equal to the integral x p x dash dx dash next order yields the ax equal to the mod px ki power minus 1 by 2 allowed region e greater than the v oscillatory and zeta equal to the p ki power minus 1 by 2 sine bracket 1 upon h integral x p plus pi by 4 forbidden e less than 4 exponential zeta equal to k minus 1 by 2 e ki power minus integral k equal to under root 2 m bracket 1 v minus e divided by h. Now quantization conditions for the bound state stay between the turning points the x1 less than the x2 and v bracket 1 x1 2 and equal to the e Bohr-Sommerfeld rule integral x1 to the x2 px dx equal to the bracket 1 n plus 1 by 2 n plus 1 by 2 pi h n comma n equal to the 0 comma 1 and Maslow index pi by 2 per turning points accurate for the high n harmonic oscillator exact tunneling and application transmission through the barrier t equal to exponential bracket 1 minus 2 integral x1 to the x2 kx dx and radial 3d effective potential v plus h square l bracket 1 l plus 1 divided by 2 mr square Langer modifications L plus 1 by 2 links to the Hamilton Jacobi S and semi-classical propagators validity and errors. Reason form condition d lambda by dx less than 1 allowed oscillatory high energy smooth v and forbidden exponential decay thick barriers turning points airy functions match connection formulas essentials. Now let's limitations of the WKB when it falls. WKB approximation fails nearly classical turning points, rapidly varying potentials where the semi-classical validity condition d lambda by dx less than 1 de Broglie wavelength lambda equal to h by p. So changes slowly breaks down turning points at the equal to the vxt local momentum. P tends to the 0, lambda tends to infinity, so mod p dash greater than the p square by the h invalidates and settes and wkb wave functions diverse p minus 1 by 2 tends to infinity. Exact solution requires a function for the linear v and v dash ext x minus xt connections formulas and the bridge reasons but fail without them. Rapidly varying the potentials, discontinuous v square Wilson barriers produce infinite force. Infinite forces f equal to the minus v dash and tends to the delta functions, violating the mod d lambda by dx less than the 1, and a high reflection occurs wkb misses the quantum interference. Thin barriers or the steep slopes amplify the error exponentially. Low quantum numbers, poor for the ground state n equal to the 0, few bound states quantizations integral p dx equal to the n plus 1 by the 2 and into the pi h inaccurate when the phase space is small and harmonic oscillators exact by the coincidence in harmonic fails early. Failure cases scenario y fails alternative turning points lambda tends to infinity area matching square potential discontinuity exact diagonalizations low n states few oscillations and numeric variationals caustics rainbows folded rays uniform wkb and the cubic terms. Now let's topic. Next topic will be what? An elementary theory. Elementary theory of the scattering, phase shift, partial waves, and Born approximations. Now elementary scattering theory expands the scattering amplitude in the partial waves using the phase shift del L K quantifying potential induced shifts outgoing waves with the Born approximation providing the perturbative estimate for the weak potentials. Now partial waves and the phase shifts. Asymptotic wave functions and zeta r and e power ikz plus f theta and ikr and further divided by the r expand in the spherical harmonics and zeta r theta and summation l to l plus 1 I to power l and pl cos theta mu l r by the kr. So radial mu L r and 10 to the sine kr minus L pi by 2 and plus delta L. Free case. Free case will be the del L equal to 0. Phase shift and for around solving the radial Schrodinger with the potential VR and a boundary mu L equal to the mu L 0 and equal to the 0 low energy S wave and delta not equal to the k minus k. So scattering length A. So scattering amplitude f theta equal to the 1 upon the 2 ik and summation L to L plus 1 e की power 2 I theta delta t minus 1 PL bracket 1 PL bracket 1 cos theta. So equal to the 1 upon k summation L and 2 L plus 1 e की power I delta L sin delta L PL and cos theta. So total cross section sigma equal to the 4 pi divided by the k square summation L bracket 1 2 L plus 1 sine square delta L optical theorem f not equal to f0 equal to the k sigma by the 4 pi. So Born approximation perturbative f theta equal to the minus m divided by the 2 pi h की power 2 integral v r e की power I q r d3 r and q equal to the k minus k dash and momentum transfer q equal to the 2k sine 2k 2k sine bracket 1 theta by 2 partial wave born 10 delta L equal to the minus 2m divided by the h की power 2 integral 0 to delta r की power 2 r की power 2 jl की power 2 k r v r dr firstborn and valid for the mod V less than the E and fails for the strong and short range potential. Example, the hardest sphere. Key relations will be the phase shift delta LK delta L less than 1 and weak V amplitude partial wave sum unitary bond Fourier transform of the V. Now next topic will be the what. Interesting. Relativistic quantum mechanics. Relativistic quantum mechanics and Kalin Gordon Darroch equation, semi-classical theory of the radiations. Relativistic quantum mechanics, Lorentz covariant wave equation, Kalin Gordon for the spin and Dirac for the spin 1 by 2, while semi-classical radiation theory treats matter quantum mechanically, electromagnetic field classically. Kalin Gordon equation starting from the relativistic energy momentum relation E square equal to the P square C square plus M square C4 substituting E equal to IH del T P tends to the IH Laplace and gives 1 by the C square D square by dt square minus Laplace square plus M square C square by H square bracket 1 the phi x equal to the 0. Kalin-Gordon equation for the scalar field of phi. It is a Lorentz invariant describe the spin O particle, but second order time derivative complicate the single particle probability interpretation, probability density, not the positive definite. So it is a mainly used quantum field theory. Direct equation, direct sought first order Lorentz covariant equation, linear time space derivatives IH and k power mu d mu and m minus mcv and the zeta x phi x zeta x equal to the 0. Gamma matrix satisfying the gamma mu and gamma v equal to the 2 neta and mu v. Squaring this operator yields the Kalin-Gordon's equation. Each spinor component satisfying the kg, and while the four component spinor structures encode spin 1 by 2 predict antiparticle, conserve current J mu and zeta and lambda gamma mu, power mu and the zeta positive J naught, restoring probability interpretation, single particle relativistic the QM. Now semi-classical theory of the radiation. Semi-classical radiation theory atoms are treated quantum mechanically, but electromagnetic field is classical wave entering by the minimal coupling P tends to the P minus QAT Hamiltonian splits h equal to h naught plus h dash t, h naught equal to the p square divided by the 2m plus vr, and h dash t equal to the minus q divided by the m a bracket 1 t into the p, and time dependent perturbation theory gives the transition amplitude between the atomic state, and this framework correctly yields the absorptions, induced emissions rates, Einstein B coefficient, dipole selection rules, and taking the classical field monochromatic. However, the spontaneous emission requires the quantization radiation field, so full quantum electrodynamics needed to compute Einstein's A coefficients. Now let's physical interpretations of the negative energy solutions in the Dirac theory. So Dirac equations, negative energy solutions are unavoidable mathematically, and their physical interpretation provided antiparticle rather than the literal electrons with the negative energy. Historically, this went through the Dirac and C pictures, now understood cleanly in the quantum field theory. Why the negative field theory? Why the negative energies appear? Free Dirac equations I h lambda I h gamma की power mu del u and minus mc zeta equal to the zero implies the relativistic energy momentum relation e की power 2 equal to the p square c square plus m square c4 plane wave solution have the e equal to the plus minus under root p square c square plus m square c4 wave equation linear both signs must be included negative energy branch extend from the minus mc square to minus infinity and direct original C interpretation single particle picture negative energy states would let an electron fall to arbitrary low energy and making the ordinary matter or unstable and direct proposals every negative energy state is already filled by an electron. Poly exclusion prevents the ordinary electrons from the decaying into them, removing one such electrons exciting it into the positive energy state leave a hole that behave as a positively charged particle with the positive energy and opposite quantum number a positron. This direct C qualitatively predicted antiparticles but is conceptually awkward. It needs an infinitely filled background special role electrons. Modern QFT interpretations antiparticles not negative energies. In the quantum field theory, the field not the particle wave function is the fundamental. The direct field is expanded in the modes with both e ki power minus iet and e ki power plus iet coefficient later interpreted creation annihilation operators antiparticles, not the negative energy electrons. States are built on the vacuum with the no particles or antiparticle. There is a no literal C. Both electrons and the positrons have the position physical energy. Negative energy solutions are the reinterpreted positive energy antiparticles moving forward in the time. Feynman and Stickelberg viewpoint. This language, mathematical negative energy branch, bookkeeping device signals, presence, antiparticles representations, Lorentz group rather than the real negative energy states. Remember, direct equation necessarily has the plus minus E solution. Single particle QM struggles, negative branch, direct C historical. In modern QFT, mods reinterpreted positive energy antiparticle eliminating unstable negative energy electrons while preserving Lorentz covariance and charge conjugations. Now that's the quantum mechanics is over. Now next topic will be thermodynamic and statistical physics. First and second order phase transitions. First order phase transitions involve the discontinuous changes, first derivatives, free energy, entropy, volume, while the second order transitions are the continuous in the first derivatives, but discontinuous in the second derivatives specific heat. First order transition, this feature latent heat L is greater than the zero and two coexisting phases separated by the discontinuous jumps in order parameter example density difference. Now Ernest, Ernest, Arnofest classification discontinuity in the G bracket 1 T comma P derivatives like the S equal to the minus del G divided by the del T comma V equal to the del G by the del P. Examples: melting, solid, liquid, boiling, liquid gas, hysteresis, supercooling, possible due to the nucleation barriers, gives free energy equal at the transitions line. Second order continuous transition, no latent heat, order parameter phi, magnetizations varies continuously through the phi t is equal to the 0, but suspectabilities diverge Cv and zeta proportional to the mod t minus tc की power minus alpha, critical point where the phases indistinguishable long range correlation zeta tends to infinity and examples Curie point ferro to the paramagnetic superfluid helium lambda transitions mean field Landau theory G equal to the alpha bracket 1 T minus Tc phi square plus B phi की power 4 phi proportional to Tc minus T की power 1 upon the 2. So comparison expect and first order, second order parameter, discontinuous jump and continuous phi tend to 0, latent heat L greater than 0, L equal to the 0, specific heat, finite discontinuity and divergence at the TC. Examples: melting point, boiling point, ferromagnetism, and superconductivity in the second order. Yes. Now the next topic coming like dimagnetism, paramagnetism, ferromagnetism. You know, it is an interesting one. To dimagnetism, paramagnetism, ferromagnetism describe the atomic scale response to external magnetic fields arising from orbital and spin contribution to the magnetic moments. Diamagnetism. All the materials exhibit the weak diamagnetism from the induced orbital currents opposing the applied field Lenz law and yielding the negative susceptibility and zeta is less than 0. No permanent moments. All the electrons paired effect vanishes when the field removed. Examples: water, copper, bismuth, superconductors, perfect diamagnetism, Meissner effect, paramagnetism. Unpaired electrons spins align weakly with the field zeta is greater than the 0, small, but the thermal disorder randomizes them above the Curie law, and zeta is proportional to 1 upon the T. No hysteresis or resonance. Examples: the aluminum, oxygen, platinum transitions, metal ions. Now ferromagnetism. Now strong zeta greater than the 1 spontaneous alignment by the exchange interaction forms the magnetic domains retains magnetizations remanence after the field removal. Hysteresis loop Curie temperature Tc Curie temperature marks Tc marks the transition to the paramagnetism. Example: iron, nickel, cobalt, gadolinium. Now comparison, suspectively, behavior in the field, examples, diamagnetic suspectibility less than 0 repel and Q, Cu, H2O, Au. Paramagnetic 0 less than zeta and less than 1 weakly attracted Al, O2, Mg. Ferromagnetic 0 zeta greater than 1 strongly attracted and permanent FINICO FENICO. Now, how temperature affects the ferromagnetism by the Curie law and Curie temperature. Temperature weakens the magnetic alignments. It reduces the paramagnetic susceptibility according to the Curie law. Destroy the ferromagnetism order at the Curie temperature above which a ferromagnetic becomes the paramagnetic. Curie law for the paramagnetism. For many paramagnetic material at sufficiently high temperature and low field, magnetization M is proportional to the field H with a suspectibility that falls as the 1 upon T. M equal to suspectibility, H equal to the suspectibility equal to the C upon the T. Now, where the C is the Curie constant, so increasing the temperature randomizes the spin orientation and weakens the induced magnetization. This 1 upon T behavior holds while the system remains disordered and near absolute zero or in a very strong fields correction appear. Curie temperature. Curie temperature and the ferromagnets. Ferromagnets have the strong exchange interactions that spontaneously aligns the spins below the critical Curie temperature Tc and giving the last temperature dependent and susceptibility remanent and magnetization. As the temperature rises towards the Tc, thermal agitation disrupts the domain alignment, magnetization of falls and the T equal to Tc phase transition occurs above the Tc material losses spontaneous magnetization behaves paramagnet with a much smaller susceptibility. Curie-Weiss law for the ferromagnets near the Tc paramagnetic region just above the Tc. Many ferromagnets follow the Curie-Weiss law. G susceptibility equal to the C divided by the T minus Tc. So susceptibility diverges as the T tends to the Tc plus reflecting onset long range order at the transition far above the Tc. The behavior approaches ordinary Curie like the 1 upon T decay thermal disorder dominates. And now the material type temperature we have a zeta key point paramagnet zeta equal to the C by T Curie law and higher T weaker M ferromagnet T less than the Tc large zeta spontaneous M order from exchange ferromagnet T is greater than the Tc zeta equal to the C divided by the T minus Tc Curie Weiss becomes a paramagnet at the Tc. Now, next topic is regarding the models. Now, Ising model, Bose-Einstein condensations. Let's deal with the Ising model. Ising model and Bose-Einstein condensations. So the Ising model mathematically describes ferromagnetism by the spins on the lattice interacting with the neighbors, exhibiting a second-order phase transition to the spontaneous magnetization below the critical temperature. Bose-Einstein condensation (BEC) occurs in the ideal Bose gases. Ideal Bose gases when a macroscopic number of the bosons occupy the ground. Bosons occupy the ground state below critical temperature, marking a quantum phase transition. Ising model Hamiltonian H equal to the minus J summation I J S I S J minus h summation I yes I equal to the plus minus 1 nearest neighbors and j greater than the 0 ferromagnetic 2D exact solution on Sager critical Tc equal to the 2j divided by the Ln 1 plus root 2 magnetization m proportional to the bracket 1 minus t divided by the tc की power 1 upon 8 bracket 1 beta equal to the 1 upon 8 mean field m equal to the 10h 10h bracket 1 beta j jdm plus bh and comma tc की power mf equal tc की power mf equal to the zj Z coordination models phase transition universally no long range order in 1D 2D at the finite t. Bose-Einstein condensations ideal non-interacting bosons below Tc equal to the bracket 1 h square divided by 2 pi m kb bracket 1 n divided by the eta and 3 by 2 की power of the 2 by 3 chemical potential mu equal to the 0 ground state of fractions n naught divided by the n equal to the 1 minus t divided by tc की power 3 by 2 no Bose-Einstein equation condensation in 2D finite n interaction stabilizes in the traps example RB87 Yankee. So order parameter condensate wave function zeta and zeta symmetry breaking U1 comparison aspect Ising model and BEC order parameter magnetization M condensate phi transition orders second continuous second off diagonal long range order now critical exponents non mean field 2D mean field like ideal gas. Now let's go deep. Compare the order parameter Ising magnetization versus BEC condensate. Ising model magnetization and BEC condensate fraction both serve as the order parameter, signaling a spontaneous symmetry breaking respective phase transition, but differ the symmetry and group and the physical nature and scaling behavior. Symmetry breaking icing monetization MSISI plus minus 1. So breaks the discrete Z2 and symmetry below TC ordered phase picks M not equal to the 0 and the Ferro disordered yum equal to the 0 para BEC condensate and a zeta equal to the under root n naught e की power I theta ground state amplitude and breaks the continuous U1 and a phase symmetry. Superfluid of phase a macroscopic a zeta is a not equal to the 0 normal fluid and a zeta equal to the 0 scaling the new critical points icing yum tc minus t की power beta equal to the 1 upon 8 exact to the 1 by 2 mean field and discontinuous suspectibility bec ideal gas now n naught by n equal to 1 minus bracket 1 t divided by tc की power 3 by 2 3d continuous but macroscopic occupation interacting the bec follows the mean field mod zeta square tc minus t Ising universal exponent from the universality class BEC ideal gas and non-universal measurement fluctuation magnetization directly average spin long range order by the correlation SISG tends to the m square condensate detected by the interference coherence of diagonal long range order zeta 0 and tends to the mod of the zeta square both the vanish above the tc comparison table feature icing magnetization m and bec condensate phi symmetry broken discrete z2 and continuous u1 scaling exponent beta 1 beta 0.125 minus zero point 0.5 and tends to the 1 ideal, mean field 1, physical meaning spin alignment and ground state occupation, transition type 2D, 3D, second order, 3D BEC, 3D BEC, no 2D, no 2D at the infinite t, no 2D at the infinite t. Now last topic will be the diffusion equation. Diffusion equations models spreading phenomena like the heat conduction, particle diffusion, or concentration gradients given by the del Tu equal to the d Laplace square u, where d is the diffusion constant. Derivation from the fixed law J equal to the minus d Laplace u flux proportional to the gradient continuity del Tu plus Laplace dot J equal to the 0 and else del Tu and equal to d and Laplace square u 1 d ut du xx fundamental solution Gaussian uxt. Now 4 pi dt minus 1 by 2 exponential bracket 1 minus x to power 2 divided by 4 dt. 2d by 3d solution radial symmetry u bracket 1 r comma t equal to 4 pi dt की power minus d by 2 exponential bracket 1 minus r की power 2 by 4 dt d dimension separation variables boundary u r comma t equal to summation e की power minus lambda n dt phi n are eigenvalues from the Laplace square phi n equal to the minus lambda n phi n steady state Laplace square u equal to 0 Laplace. Now key properties aspect feature green function Gaussian variance 2 dt dimensions no steady state in the infinite domain numerics explicit implicit finite differences. Now here is the next topic will be the random walk and the Brownian motions. The random walk and the Brownian motion is the random walk model stochastic particle motion with the equal probability steps and covering to the Brownian motion in the continuum limit, both underpinning the physics diffusion equation del Tu equal to the d Laplace square u. Now random walk. Discrete the 1D particle at the integer side jumps left and right with the probability 1 upon the 2 each delta t Poisson after the n steps mini x equal to the 0 variance x square equal to the n into the delta x square equal to 2 dt bracket 1 d minus delta x square divided by 2 delta t. So probability p bracket 1 x comma t obeys the master equation continuum limits L diffusion equation center limit theorem Gaussian distribution Brownian motion continuous limit random walk position xt follow the Langevin equation x dot equal to under root 2d zeta t and zeta is white noise bracket 1 zeta t and into zeta t dash equal to delta bracket 1 t minus t dash mean square displacement angular bracket x t minus x naught square equal to 2d dt 2d dt bracket 1 d dimension probability density p bracket 1 x comma t equal to 4 pi dt की power minus d by 2 exponential minus r की power 2 by the 4 dt exact green functions. Now diffusion equation connections to the diffusions. Connections to the diffusion, random walk probability Pn m steps right of n total, diffusion equation delta x delta t tends to the zero, d fixed and the Brownian paths are Wiener process of fractal dimensions too. Key properties expected random walk and a Brownian motion. Aspect x squared 2 dt and 2 dt. So path nature, discrete jumps and continuous, nowhere differentiable. Applications polymer finance, collide physics. Now the last topic of the thermodynamics and statistical physics will be the introductions to the non-equilibrium process. Non-equilibrium process describe the system driven away from the thermodynamic equilibrium by the external flexors of the energy, matter, or the momentum, leading to the irreversible evolution, entropy, production, transport phenomena, diffusion, or the heat flow. Key characteristic system exchange energy matter with the surroundings, open system preventing relaxation, uniform equilibrium states, local thermodynamics equilibrium hold variables like the dp well defined locally but a global gradient persists. Entropy production sigma equal to summation ji xi greater than 0 fluxes j time forces x and dictates directionality per second law extension. Linear response resumes near the equilibrium fluxus linear forces Jacobian equal to Lx on Sager coefficient L and symmetric by the reciprocity. Example Fourier's JQ equal to the minus k and the delta t and the fic and j and fic will be the jn equal to the minus d and the d and ohm Je and sigma E and the pre-Gaussian minimum entropy productions for the steady states. Far from the equilibrium phenomena, nonlinearities yield the self-organization Bernard cells heat convections patterns. Belousov and Zahabotinsky reaction oscillation during the patterns and fluctuations dissipations theorem breaks the large fluctuation amplified near the instabilities. So comparison regime behavior examples near equilibrium, linear stable steady and heat conductions far from the equilibrium, nonlinear patterns, convections and chemical waves. So thus the thermodynamics and statistical physics is over. Now the topics electronics and experimental methods. Now next topic with the linear and the non-linear Non-linear curve fitting chi-square test. Linear curve fitting use the least square minimize the residual models like the y equal to the mx plus c while the non-linear fitting handles complex the functions by the iterative and optimization. Chi-square test goodness of the fit by comparing observed versus expected data. Linear fitting for the data xi yi minimize chi square equal to summation bracket 1 yi minus bracket 1 mxi plus c की power of the 2 divided by the sigma I की power 2. Closed form m equal to the n bracket 1 summation xy minus summation x summation y divided by the n into the summation x की power 2 minus bracket 1 summation x की power of the 2. So c equal to the y bar minus mx bar equal to into the errors from the covariance matrix assume the Gaussian noise. The nonlinear fittings models y equal to fax example Gaussian exponential iterative and Leeuwenberg Mark coordinate. Leeuwenberg Mark coordinate updates an plus 1 equal to an minus j की power t j bracket 1 minus 1 j की power t r Jacobian j ix equal to df divided by the d del aj converges to the local minimum needs good initial guess and bounds. Chi square test goodness of the fit. Chi square equal to summation order oi minus ei की power 2 by ei degree of the freedom n minus p minus 1 p parameters reduce xv cheap v squared equal to 1 good fit p value from the cdf test and null data matches models independence contingency tables comparison method model type solutions and use cases linear straight analytic simple trends non-linear curved iterative growth fix chi square equal to any statistics and model validations. Our next topic will dealing with the transducers, temperature, pressure, vacuum, magnetic fields, vibration, optics, and the particle detectors. The transducers convert the physical quantities into electrical signal for the measurement and the control. Common examples include the temperature, pressure, vacuum, and magnetic field vibrations, opticals, and the particle detectors. Temperatures and the pressure vacuum. Temperature is a thermocouple, CVAC effect, wide range, fast and rugged RTD, resistance versus temperature, high accuracy, narrower range, thermistor, semiconductor, high sensitivity, limited range. Now pressure, vacuum, strain, gauge, diaphragm, resistive change under the deformation, piezoelectric sensor, dynamic pressure, vibration, capacitive, and piezoresistive. MEMS for the low high pressure ranges, magnetic vibration and optical. Magnetic field Hall effect senses voltage proportional to V flux gate magnetorestrictive devices, vibrations or acceleration, piezoelectric accelerometer, seismic mass with a capacity of the inducive pickup, LVDT for the displacement, optical photodiodes, photomultipliers, CCD, CMOS, imagers, fiber optic sensors for the temperatures, pressure, using intensity, phase, are the polarizations, modulations. Now, particle detectors, gas filled ionization chambers, proportional counters, Geiger Muller tubes, charge from the gas ionization, scintillation detector, scintillator plus photo multiplier or photodiode light pulses from the radiation semiconductor detectors silicon germanium electron hole pairs from the ionizing particles excellent energy resolution. Now the quantity and typical transducer. Temperature is a thermocouple, RTD, thermistor, pressure, vacuum, strain gauge, piezoelectric, capacitive, magnetic, Hall, flux gate, magnetoresistive, vibration is the piezo accelerometer, LVDT, optical photodiode, PMT, CCD, CMOS, particles, GMTU, proportional, scintillator, and semiconductors. Measurement and the control. Measurement control combines sensing, decision making, actuation, keep the physical variables temperature, pressure, and speed and desired values within the safe range. And measurement is converts the physical quantities calibrated the electrical signals by the transducers and instrument accuracy, precision, resolution, linearity, and response time characterize the measurement quality. Now, signals may be analog, voltage, current, digital, ADC sampled, often a pass through the conditioning and amplification, filtering, isolations, and before the processing control system control the compares measured variable reference set point adjust actuators to reduce the errors. Open loop is the no feedback output not corrected. Example the fixed time motor run and closed loop feedback controller uses sensor feedback compute. The control action standard is the PID control with the proportional integral and derivative terms shaping the response and speed overshoot and steady state error. Component measurement control loop sensor transducers measures the process variables signal conditioning and the ADC prepare the signal for the controller analog digital implement control the law on off PID and model based actuators are the bells heaters motors pumps etc that influence the process. Now human machine like interface data logging for the monitoring and the tuning. Applications industrial temperature pressure control in the reactors of flow and level control and in the pipelines laboratory and the physics stabilize the laser intensity frequency vacuum pressure regulations and everyday system thermostats cruise control and automatic brightness and autofocus in the cameras. Now, next will be the signal conditioning and recovery. Signal conditioning prepares the raw sensor outputs accurate measurement control, while the signal recovery aims to reconstruct and desired underlying signal from the noisy or distorted measurement. Signal conditioning typical functions amplification, attenuation, match the sensor levels to the ADC or the instrumentation range, or improve the signal to the noise ratio, filtering low pass to remove the high frequency noise, high pass to remove the DC drift, band pass or notch to isolate. Notch to isolate specific bands 50 to 60 hertz means rejection, isolation and the protection. Opto transformer isolation, surge and over voltage protection, preventing ground loops, linearizations and convergence, mapping non-linear sensor responses, thermocouple thermistors to the linear signals, current voltage or resistance voltage convergence. Example, Wheatstone bridge. Signal recovery given the conditions but noisy signals recovery techniques extract the underlying waveform or features time domain denoising averaging, moving averages, adaptive filters, frequency, time frequency methods, Fourier or wavelet filtering, remove known noise, bands, spectrograms, scaleogram, best reconstructions, model based optimization, fitting parametric models, noisy data using algorithms, Wanner filtering, modern gradient descent, phase retrieval, and reconstruct the signal from the incomplete or the magnitude of the measurement. The practical chain sensor signal conditioning amplify the filter isolate linearized ADC digital processing signal recovery denoise denoise and deconvolve and deconstruct reconstruct feature extraction control decisions. Now, next topic will be the impedance matching and amplifications OP AMP based instrumentation AMP feedback filtering and the noise filtering and the noise reductions impedance matching amplification feedback filtering noise reduction together ensure that the sensor signal chains deliver accurate, undistorted, low noise signals to the later stages like the ADCs or the control logics. Impedance matching designs source load impedances to maximize the power transfer or minimize the reflections crucial in RF and a high speed circuits for maximum power. The load is a complex conjugate source JDL equal to the JDS star conjugate matching. Now for the minimal reflection on the transmission line JDL equal to the JDS reflectionless matching low frequency instrumentation and high input impedance amplifiers OPAMPS often used to avoid loading sensors rather than strict matching amplifications feedbacks. Now the own OPMP based amplifiers non-inverting AV equal to the 1 plus RF by the RG, inverting AV equal to the minus RF by RIN, high input impedance and low output impedance with the negative feedback for linear and stable gain. Instrumentation amplifiers 3OP AMP structures with a very high common mode ejection and stable accurate gain for the small differential signals example bridge sensors or the ECG feedback negative reduces the gain sensitivity distortions bandwidth variations sets predictable input or output impedances positive feedback used in the comparators oscillators filtering the noise reductions filters save bandwidth to the pass desired signals reject the noise active filters OPAMP plus RC low pass high pass band pass note 50 to 60 hertz hum removal and with a controlled gain and sharpness. Noise reductions minimize resistor values consistent with the power limits. Choose the low noise OPAMPS narrow bandwidth just above signal spectrum noise power band proportional to bandwidth and use the shielding and a proper grounding fight EMI sometimes aided differential measurement plus the instrumentation AMPS reject the common mode noise. Topic key goal typical techniques impedance matching maximum power low reflection conjugate or equal Z. Now amplification set gain Set again high input JED OPAMP instrumentation AMP feedback filtering bandwidth shaping active RC filters notch noise reductions improve SNR low noise parts narrow BW and the shielding. Now next topic will be shielding and the grounding. Shielding, grounding work together, protect signals, equipment. Grounding provides the safe reference fault paths while the shielding blocks and or diverts the electromagnetic interference EMI. Grounding basics, earthing ties the conductive parts to common reference of an earth to provide a low impedance path for the fault currents, enhancing the safety, stabilize the reference potential, improving the signal integrity and reducing the EMI. Good practice: use the star signal point grounds, prevent ground loops, and keep ground connection short and wide to the lower inductance and separate noisy power grounds from the sensitive analog or the digital grounds, joining them at one control point. Shielding uses the conductive magnetic enclosures cable sealed to the block electric or the magnetic fields from entering or leaving the sensitive circuit. Example: metal ensures the braided or the foil cable sealed RF gaskets and seals are usually bonded to ground so that the induced current are safely diverted, instead coupling into the signal conductors, avoiding the ground loops and best practices. Now the ground loops occur when the multiplying ground path from the loop allowing the circulating the currents and a human noise. A typical strategies and a cable sheets are bounded at one end, often at the instrument and the control side for the low frequency analog signal. For the long or the high frequency cables, sometimes ground at the both end for the better RF performance, but designed carefully. Maintain the sealed continuity, use the 360-degree terminations, connections, keep a sensor ground isolated from the noisy chassis ground when needed. So, aspect and a purpose, a key techniques, grounding, safety, reference, EMI control, star ground, short, wide paths, and separate analog or digital grounds. Shielding is the block into or out of the circuits. Metal enclosures, shielded cables, proper sealed bondings. Now next topic will be what? Let me guess. Fourier transforms lock-in detector. Fourier transform decompose signals into frequency components, while the lock-in detector use the phase-sensitive detection at the chosen reference frequency to extract the teeny signals buried in the noise. Fourier transform continuous Fourier transform time signal xt is the x bracket 1 omega equal to the integral minus infinity to infinity x t e की power minus I omega t dt, mapping the time domain data complex frequency domain amplitudes phases. Inverse the transform reconstruct x t from x omega properties like the linearity convolution theorem convolution in the time, multiplication, frequency, Parseval theorem, energy conservation, make it a center for the filtering and spectroscopy solving the differential equation. Lock-in detector, lock-in amplifier. A lock-in amplifier multiplies input signals by the reference sinusoid frequency F reference and a low pass filters product yielding the DC output proportional to the component input F reference with the specific phase. Input ST equal to the A cos bracket 1 omega t plus phi plus noise reference RT equal to the cos omega t multiply ST into RT produces a term proportional to the cos phi at the DC and the terms at the 2 omega. Low pass filter. Low pass filter removes the 2 omega and broadband noise, leaving a DC proportional to the signal amplitude and cos phi. Dual phase lock. Dual phase lock in use both in the phase and the quadrature references to recover the amplitude and a phase fully. Now combined use in experiments. Fourier analysis characterizes the signals spectra and the noise bands guiding the choice of modulations and the lock in the reference frequency where the noise in the minimal and lock in a detection then a narrow effective bandwidth around the F reference, greatly improving the signal to the noise ratio for the weak periodic signal example chopped light in the optical experiment. Now then further we will boxcar integrator and modulation techniques. Boxcar Avenger, gated integrator, and used to extract weak and pulsed signals, noise modulation techniques, AM, FM, PM, encode information onto carrier by varying the amplitude, frequency, phase. Boxcar integrator samples integrates input only during the narrow time gate, synchronized to a trigger, then average over the many repetitions. Operations after the trigger, a delay sits when the gate opens during the gate with the delta T at RC integrator accumulates the signals. Output is the proportional to the average signals in that window. Benefit noise outside the gate most of the time to low duty cycle pulses is largely rejected, improving the SNR by the roughly under root T by delta T where T is the period. This is ideal repetitive pulse experiment, pump probe optics particle detections. Modulation techniques. Modulation shift information to a carrier frequency where the transmission detections are easier and noise is lower. Amplitude modulation AM carrier amplitude. Carrier amplitude varies with the message frequency phase fixed. Phase fixed, simple but sensitive to the amplitude noise. Now frequency modulation, carrier frequency varies with the message, amplitude constant, more robust to the amplitude noise and used in the radio telemetry. Pulse modulation PM. Carrier phase varies with the masses, amplitude, and nominal frequency, constant closely related to FM, both the underlie many digital skim PSK FSK. In the precision's measurement, modulating a signal, chopping the light intensity or the current, move it to known frequency band and a band card or the lock-in detection at that frequency, then recovers the signal with the high SNR. There will be the next topic will be the high frequency devices. High frequency device generates, manipulates, detect RF microwave signals using specialized oscillators, amplifiers, detectors optimized for the gigahertz range operation. High frequency generators, RF and microwave signal generators produce the sinusoidal pulsed modulated signals for the testing, communications, radars, high speed electronics and core element oscillator, LC crystal, VCO synthesizers, whose frequency is controlled optically optionally, phase locked at the microwave frequency, gun diode oscillators exploit negative differential resistance in a gun diode to generate the stable gigahertz signal for the radars, guns, and sensors and local oscillators. High frequency detectors, RF detectors, convert the RF powers into DC voltage, typically using the fast diodes Schottky and followed by the RC smoothing. Output is proportional to the RF and amplitude of the power used in the power meters. So here AGC loops and spectrum analyzers. Other detectors includes Schottky diode mixers for the down conversion to IF, bolometers, and thermocouple sensors for the precise power measurement. Heterodyne receives combining the local oscillators and mixers for the sensitive detections. Device types and uses the device type example technologies and main use. RF signal generator, synthesizer, VCO, test calibrations, communications, microwave oscillators, GAN, DRO, PLL source and radar, local oscillators, RF detectors, Schottky diode, bolometer, power monitoring, AGC sensing. Now the mixer, receiver, Schottky mixer plus LO frequency convergence and demodulations. Now thus the electronics and experimental method is over. Now the next topic will be atomics and molecular physics. Our next topics will be the quantum. Quantum states of electron in an atom, electron spin, and spectrum of the helium and alkali atom. Quantum state electron atom described four quantum numbers principal n, orbital n, magnetic ml, spin ms plus minus 1 by 2. Electron spin introduces intrinsic angular momentum leading to the fine structure spectra like the helium single, triplet, and alkali atoms doublets. Electron quantum states and spins. Schrodinger equation yields the hydrogenic orbitals zeta n l m l r theta phi equal to r n l bracket 1 r y l m y l to the m l theta and the phi. Pauli principles. No two electrons share all the four numbers. Spin s equal to the 1 upon 2, ms equal to the plus minus 1 by 2 up or down from direct equation. Stern and Gerlach splits the beams and total angular momentum J equal to the L plus S. Now helium spectrum, two electrons ground, one s2, one s not excited perihelium, singlet antisymmetric spin S equal to the 0 and the orthohelium triplet S equal to the 1, singlet sharp and similar penetration triplet diffuse exchange. Fine structure JL equal to the L plus minus 1 by the 2 splits levels and selections. Delta S equal to the 0, delta L equal to the plus minus 1 comma 0. Intercombination weak alkali atoms one valence electrons like the hydrogen but screened core and spectrum resembles H, but scales En proportional to the minus 1 upon N k power 2 effective. Fine structure prominent 2 S 1 by 2, 2 P 1 by 2, 3 by 2 doublets. Doublet is the normal multiplet J equal to the L plus minus 1 by 2 sodium D minus 3 2P3 by 2 minus 3 2P S1 by 2 589 point 0 nm and 3 ki power 2 p ki power 1 by 2 and minus 3 ki power 2 s ki power 1 by 2 589.6 nanometer comparison atom system key features and spectral signature helium single triplet annexation sharp diffuse series alkali now one electron fine structure doublets spd. Now, yes, the next topic will be the what? Relativistic corrections for the energy levels of the hydrogen atoms, hyperfine structures, and isotropic shift, width of the spectrum lines, LAS, and the JJ couplings. Relativistic corrections and hyperfine structure, isotropic shifts, and line widths refine the hydrogen energy levels beyond non-relativistic and shorten the solution with the LS and the JJ couplings describing the multi-electron angular momentum. So relativistic corrections. Now the fine structure combines the relativistic kinetic energy delta E relative equal to the minus E n की power 2 divided by the 2 mc square bracket 1 upon n square plus alpha square into z की power 4 divided by n की power 4 and spin orbit HSO equal to the L dot S divided by the 2 m square c square r into dv divided by the dr. Total shift will be the delta E fs equal to the E n En alpha square z की power 4 divided by the n cube bracket 1 upon j plus 1 by 2 minus 3 divided by the 4n independent of the L. Lamb shift QED further splits 2s 1 by 2 2p 1 by 2 hyperfine and isotopic effects. Hyperfine Fermi contact plus dipolar interaction between the electron and the nuclear spins splits the ground states H21 centimeter line delta E HF proportional to the GP mu n mu b by a naught cube 5.9 into the 10 to the power minus 6 electron volt. So isotopic shift and mass difference change reduce the mass mu, nuclear sizes yielding the normal mass, specific volume shifts, and H versus D lines separate by the point 1 centimeter minus 1. So spectral line width, natural line width from lifetime uncertainty delta E delta T and H Lorentzian profile delta mu by equal to A divided by the 2 pi and A Einstein coefficient. Now the typical 10 megahertz allowed transition Doppler broadening adds Gaussian thermal with delta VBD D and V naught equal to the under root 2 kT by the MC square. LS equal to the LS and JJ couplings. LS is the Russell and Saunders. L equal to summation Li S equal to summation Si, and then J equal to the L plus S, light atoms and weak SO, JJ individuals, Ji equal to Li plus Si. Then the Z equal to the summation Ji. Heavy atoms, strong SO, intermediate coupling mixes. Effect summary correction scale EH and physical origin. Fine structures alpha की power 2 10 the power minus 4 relative plus SO. Hyperfine alpha की power 4 m 10 the power minus 6 nuclear spin isotopic shift and m divided by the m 10 the power minus 4 mass or radius natural width 10 the power minus 7 lifetime. No, it is a good one. G-Man and the Paschen, Batch and Stark effect and electron spin resonance. So G-Man, Paschen, Bach and Stark effect describe spectral lines splitting under the external fields while the electron spin resonance ESR probe spin transition in a magnetic field. G-Man and the Paschen, Bach effects normal G-man Wick B. Wick B singlet states orbital G main delta E equal to the mu B MLB splits a line into the three transverse or one longitudinal pi anomalous includes spin G equal to the 2 delta E equal to the mu B G J M J B complex multiplates partition back strong B uncouples LS levels follow the individual MLMS linear G man regain star if Stark effect electric field F splits degenerate levels by the H dash equal to the minus D dot F dipole linear star hydrogenic degenerate N quadratic matrix diagonalization lift degeneracy permanent dipoles absent quadratic star non-degenerate example the ground second order perturbation delta E proportional to the minus alpha f की power to polarizability alpha electron spin resonance ESR microwave absorption induces delta ms equal to plus minus 1 transitions in the paramagnets h mu equal to the g mu b b and bracket 1 g equal to the 2 b equal to the 0.3 t and x band 9 gigahertz hyperfine splitting from the nuclear spins now H doublet used for the free radical defects line widths from the relaxation effects comparison effect field type splitting origin regime G-man magnetic orbital spin moment wick B and Paschen back magnetic decoupled LAS strong B Stark electric dipole interaction linear quadratic ESR microwave spin flips and resonance. Oh yes. Now the next topic is nuclear magnetic resonance chemical shift Frank Condon principle born Oppenheimer Born Oppenheimer approximation. Nuclear magnetic resonance (NMR) proves nuclear spins magnetic fields with the chemical shifts revealing the local environment. Frank Condon principle governs the vibronic transition Born Oppenheimer approximation separates nuclear and electronic motion. NMR and the chemical shifts. Now NMR nuclei with the spin I greater than the zero. Example Hi equal to the 1 upon 2 split in the magnetic field by the G meant delta E Z mu N M I B RF equal to the pulse flip. Pulse flips spins. Relaxation here the signals. Chemical shift delta equal to the bracket when V minus V reference divided by the V naught ppm from the electron shielding, de-shielding, electromagnetic and neighbors shift downfield greater than TMS 0 ppm. Example CH3.9 CH2 Cl 3.5 ppm. Frank Condon principle. Vertical electronic transition fixed nuclei dominate UV and the vis absorptions and emission due to the fast electron 10 to the power 5 minus 15 years vs now the solar slow nuclear vibration 10 to the power minus 13 second overlap vibrational wave functions gives the Frank Condon factors maximum intensity where the tuning points aligns explaining the vibrational progressive and Stokes shifts. Born Oppenheimer approximation, electrons adjust instantly to the nuclear position ME less than MN and solve electronic Schrodinger for the fixed R, get the EL bracket 1 R plus V and N R equal to the E total R. Then the nuclear motion on this surface, vibration, rotation, breakdown nuclear, breakdown near the conical intersections enables the molecular orbital theory, comparison concept, key physics, and spectroscopy role. NMR chemical shift, electron shielding structural ID. Frank Condon vertical transitions and vibronic intensities. Born Oppenheimer. Now the mass separations and potential surfaces. Yay! Now the next topic will be what? Electronic, rotational, vibrational, and the Raman spectra of the diatomic molecules. Diatomic molecules exhibit electronic UV, VIS, and the rotational, microwave, vibrational IR Raman spectra governed by the energy level from the Born Oppenheimer separation selection rule from the dipole, quadruple, and transition rotational vibrational spectra and the rotational levels ej equal to the bj bracket when the j plus 1 rigid rotors b equal to the h divided by the 8 pi square lc microwave absorption delta j equal to the plus minus 1 and vibrational ev equal to h mu bracket 1 mu plus 1 by 2 harmonic ir equal to ir delta v equal to the plus minus 1 ro vibrational irp bracket 1 delta j equal to the minus 1 q equal to q bracket 1 delta j equal to the 0 sometimes forbidden. Now r delta j plus 1 branches around the band origin bar and nu is the 0 electronic spectra UV vis transition between the potentials and the Frank Condon vertical transition maximize and progressions. And V equal V double dash 0 V dash and turning point overlap rotational fine structure within the bands. Raman spectra inelastic the light and scattering stocks delta V minus 1 anti stocks. Now the Y the delta V plus 1 vibrational pure rotational and delta Z plus minus 2 Forbidden IR homonuclear and rotational vibrational Raman and OPQR S branch and polarizability chain require the no dipole. So selection rule summary spectral type delta V delta Z polarization other rotational 0 plus minus 1 mu permanent vibrational plus minus and 1 0 mu chain RO vibrational IR plus minus 1 1 0 plus minus plus 1 electronic greater than equal to the 0 minus 1 plus 1 allowed uh, summation and angular. Now the Raman plus minus 1 0 plus minus 2 and alpha change. Now the next topic will be the lasers, spontaneous and stimulated emission Einstein A and B coefficients. So lasers rely on stimulated emissions dominating over spontaneous emission through the population inversion quantified by the Einstein A B coefficient relating the transition rates. Spontaneous and stimulated emission. Spontaneous emission excited atom randomly decay to the ground state emitting photon energy h mu equal to E2 minus E1 arbitrary direction fade stimulated emissions incoming photon exact h mu triggers identical photon from excited atom same frequency phase direction polarization amplifying the field and absorption ground state atom absorbs the h mu photon exciting to the upper level Einstein coefficient two levels, one ground, two excited rates per atom, spontaneous A21 S minus 1 stimulated emission absorption B21 minus B12 depends on the radiation density mu V. Equilibrium N2 A21 equal to the N1 B12 and the U and the V yields the Planck UV and equal to the 8 pi h mu cube divided by c cube equal to into the 1 divided by the e की power h mu by the kt minus 1 with the a to 1 by the b to 1 and equal to the 8 pi h mu cube by the c cube. Lasers requires the n2 by n1 and inversion stimulated emission greater than the absorption to laser operations, pumping creates the inversions, initial spontaneous emission. Emission seeds the coherent stimulated emissions in the optical cavity, mirror selective modes, and gain greater than losses above the threshold output monochromatic directional coherent light coefficient comparison process rate directionality and laser role. Now spontaneous A N2 A21 random seeds cavities stimulated B. Now N2 B21 mu U and V coherent amplification absorption B N1 B12 and UV none and limits again. Now next topic will be the optical pumping. Optical pumping, population inversion, rate equation, modes of the resonators, and coherence length. Optical pumping excites the laser media to achieve the population inversion analyzed by the rate equation while the resonator modes determine the laser frequencies and coherence the light. Coherence the light measures temporal coherence, optical pumping, and the population inversion. Optical pumping uses the light flash lamps and diodes to promote the atoms or ions from the ground state to the higher level, creating the inversion between the lasing levels and three levels is the ruby pump broad upper and fast decay to the metastable E2 inversions on the E2 tends to the E1 If the lower level decays quickly, four levels NDYAG pump E4 to the E3 metastable. E2 decays. E2 decays the fast to the ground, easier inversion even at the low pump rates. Now the rate equations. Rate equation for level d n 3 by dt equal to nrp bracket 1 n1 plus n2 plus n3 plus n4 minus n3 by t3 n3 by the tau 3 minus sigma 3 2 and I into n3 minus n2 etc steady state inversion delta n equal to n3 minus n2 rp tau 3 small n2 threshold gain G equal to sigma delta n L and greater than losses. Resonator modes and coherence Fabry parrot cavity modes frequency VQ equal to the QC divided by the 2L longitudinal Q transverse stem and the mode spacing delta V equal to C divided by 2L coherent length LC equal to the C divided by delta V line transform limited and line width from the gain and inhomogeneity long LC for the single mode operation comparison aspect and three level and four level inversion erase hard and deplete ground EG. Now pump efficiency lower and higher threshold higher or lower. Thus, the atomic and molecular physics is over. Now, next topic is the condensed matter physics. Condensed matter physics. The topic is Bravais lattices, reciprocal lattices, and diffraction, and the structure factor and bonding of the solids. So Bravais lattice classify crystal symmetries into the 14 types, and reciprocal lattice enable the diffractions analysis. The structure factors determined allow the reflections. Bonding types dictate the solid properties. Bravais lattices are the infinite arrays of point identical environment defined by the primitive vectors A1, A2, A3, 14 types, 3D, 7 system, cubic, tetragonal, etc. Into 2 bracket 1 primitive P body centered L and face centered F and base centered C example FCC and 4 atom per unit cell at the 000 and 1 by 2 1 by 2 0 etc BCC 2 atoms reciprocal lattice vectors b1 equal to the 2 pi into the a2 into a3 divided by the a1 a2 cross a3 divided by the a1 dot bracket 1 a2 cross a3 cyclic planes g equal to the g equal to h b1 plus k b2 plus l b3 h b1 plus k b2 plus l b3 satisfy the Bragg 2d into k equal to 2 pi log scattering vector equal to the scattering vector q equal to the kf minus ki equal to the g for diffraction diffractions and the structure factor x-ray neutron diffraction intensity I proportional to the mod FHKL square structure factor FHKL equal to the summation j Fj e की power I j R j F atomic form factor systematic absence Example FCC F and 0 unless HKL all even odd and Brillouin John first Wigner and cities cell reciprocal lattice bonding in the solids type example properties ionic NaCl brittle high melting covalent diamond silicon hard directional metallic copper aluminum ductile conductive molecular ice soft low melting van der Waals, noble gas, weak and low density. Now, next topic will be the elastic properties, phonons, lattice specific heat, lattice specific heat, free electron theory, and electronic specific heat response and relaxation phenomena. Elastic properties relate to the lattice vibration. Phonons contribute specific heat by Debye theory, free electron theory explains the electronic specific heat linear in the T response phenomena involve the dielectric conductivity under the fields with the relaxation times. Elastic properties and phonons. Elastic constants. Bulk modulus B, shear mu from the interatomic potential sound speed C equal to under root B divided by the rho for phonons. Quantized lattice mods. Now dispersion omega q lattice dynamical matrix dB model linear omega equal to the VQ to cut off the omega D3 and modes and specific heat CV equal to the 9 N kBT divided by theta D keep power 3 integral 0 to the theta D divided by the T x ki power 4 e ki power x d and divided by the e ki power x minus 1 ki power 2 dx and the theta D h omega D by the kb low T and T ki power 3 high T DeLong the Petit. Now free electron theory, electronic specific heat. Drude Sommerfeld fermions fills to Fermi energy EF density states GEF 3n divided by 2 EF only electrons within the KBT and of the EF excited CEL gamma T and gamma pi square by 3 K square BG and EF pi square by 2 NKB KBT by the EF much smaller than the for the room and the T dominates at the MK. Response and relaxation. Linear response dielectric E eta omega equal to eta infinity plus G divided by 1 minus I omega T. Now conductivity equal to the sigma omega and the sigma naught divided by under 1 minus I omega T tau. So Drude, relaxation time tau equal to the L divided by the VF and mean free path of the L. So photon, drag, polaron, and effect modify AC respectively and shows the dispersion near the 1 by tau. Specific heat contribution, temperature regime, dominant term scaling, T theta D, T less than theta D, phonons, T ki power 3, T mk electrons, T theta D, DeLong Petit constants. Drude model of the Drude model of the electrical and thermal conductivity, Hall effect and thermoelectric power. Drude model Drude model treats conduction electrons classical gas with the collision, predicting DC electrical conductivity sigma equal to the n e square tau divided by the m thermal conductivity k equal to the 1 upon 3 n into the v square tau cv with the Widman French log L equal to the k divided by the sigma t equal to the pi square divided by 3 bracket 1 kb divided by the e ki power 2 Hall effect measures carrier type density by the transverse voltage thermoelectric power Seebeck and gives the voltage from the temperature gradient. Drude conductivity electron drift with the velocity Vd equal to the minus eta and E tau by the m under the field E relaxation time tau current J equal to the minus n EVD so sigma equal to the n E square tau divided by m thermal hotter electrons carry more energy net flux jq equal to the minus 1 by 3 V square and tau CV del T and K 1 by 3 N V square tau CV 3 by 2 kV. Now temperature dependence rho proportional to the T phonon scattering. Hall effect crossed E and R fields Lorentz force balancing eta EH equal to the EVDB Hall field EH equal to the Hall field EH equal to the JB divided by the N eta and coefficient RH equal to the 1 upon NE positive for the holes measures N distinguishes electrons or holes. Now thermoelectric power Seebeck del V equal to the S del T and comma S equal to the minus bracket 1 pi square kb square divided by T pi square kb square T divided by 3e into ef diffusion of the hot electrons positive for the p type negative n type used in the thermocouples comparison property Drude expression key parameters electrical sigma n e square tau divided by the m mobility thermal k equal to the 1 thermal k equal to the 1 upon 3 v square tau cv n and heat capacity hall or h 1 upon any carrier density Seebeck yes alpha T divided by the EF Fermi energy. Now let's the next topic will be the electron motion in the periodic potential band theory of the solids and band theory of the solids metals insulators and semiconductors. Electron motion in the periodic potential leads to the energy bands by the Bloch theorem distinguishing metals partially filled bands insulators filled the bands with the large gaps and semiconductors small gaps with the thermal activation Bloch theorem and the bands Bloch waves zeta r mu r ikr mu is the periodic and nearly free electron model periodic V opens a gap at the Brillouin zone boundaries. Now the k equal to the pi by a by the Bragg reflection tight binding atomic orbital overlap forming the narrow bands and the ek equal to the e naught minus t cos ka. Now the classification metals bands overlap or partially fill the Fermi level and conduction is the CUSP overlap insulators. Now filled a balance band empty conduction band large gap easy greater than 5 electron volt diamond 5.5 electron volt semiconductor small eg zero point 0.1 to 3 electron volt silicon 1.1 electron volt and intrinsic thermal excitation doped NP type donors acceptors near the band edges. Now band structure features Fermi surface constant energy in the k space effective mass m star equal to the h square divided by the del square e by del k square direct indirect gaps affect the optical transition classification tables material band filling a gap conductivity examples metal partial overlap high sodium copper insulator filled plus large gap and zero NaCl diamond and now the semiconductor filled plus small gap moderate tunable SIGAS. Now, next topic will be superconductivity type 1, type 2, superconductors, Josephson Johnson superfluidity. Superconductivity features zero resistance and perfect diamagnetism below critical temperature. TC type 1 superconductors abruptly lost the superconductivity above the single HC, while the type 2 exhibit the vortex mixed states between HC1 and HC2. Josephson Johnson enabled the tunneling currents between the superconductors and superfluidity and shows the dissipation less flow in the for helium below the 2.17 K. Now the type 1 versus type 2 semiconductor superconductors. Type 1 is the pure metals like the lead. Tc less than 10 K complete Meissner effect. Lambda less than zeta, K less than 1 by root 2, sharp normal transition at the HC. Type 2 alloys like the niobium, titanium, Tc greater than the 10K, partial Meissner, Bragg-Edmond lambda greater than zeta, and K greater than the 1, divide by the root 2. Flux penetrates now the abricosal vortices in the mixed state HC1 less than H less than HC2, enabling the high field application MRI. Josephson Johnson's weak ink thin insulator between the two superconductors. DC Josephson effect equal to IC sine delta phase difference delta AC affect the voltage V and to EV and HD delta T by dt. Now G gigahertz oscillation application squids magnetic sensing qubits. Now superfluidity 4 helium 2 bracket 1 T less than the T lambda 2.17 K. Two fluid models normal superfluid components, zero viscosity and quantized vortices k equal to h by 2m, analogous to superconductivity BCS pairs, and that is a Cooper pairs. Now the comparison. Phenomenon key feature example type 1 SC, SARP, HC, pure Meissner, Mercury, HgAl, type 2 SC, vortex state, high HC2, NB3, SN, YBCO, Josephson, tunneling, phase coherence, Squid, Johnson, superfluidity, mu, superfluidity, rho s greater than 0, no viscosity, 4 helium dilute, BEC. Now, next topic will be the what? Defects. Defects, dislocation, order, phase, matter, translational orientation, order, kinds, liquid crystalline order, quasi-crystals. So defects and dislocation control many mechanical, electronic. Yeah, it is interesting one. Good one. Excuse me a moment. We come back. Yes, nice. Defects, dislocations, and order phases matter. Translational orientation, order kinds, and liquid crystalline order quasi-crystals. Defects and dislocation control many mechanical electronic property crystals, order phases, liquid crystal, quasi-crystals, generalized crystalline order beyond the simple periodic lattice. Defects, dislocation, crystalline defects classified by dimensionality, point defects, vacancies, missing atoms, interstitial extra atom between the lattice sites, substitutional impurities, ionic, Frankel, or Schottky defects. Now the line defect, dislocation is dislocation, extra half-plane atoms ending inside crystal and screw dislocation, helical distortions, and the most real dislocations are the mix, and their strength is given by the Berger vector which measure the lattice distortion around the line, and a planar defects, grain boundaries, twin boundaries, stacking faults, dislocations enable the plastics and deformation at the stresses far below the theoretical shear strength and strongly affect yield strength, work hardening and diffusion, translation and orientational order, translational order, regular repetition, position, perfect crystals have the long range translational order in all the three dimensions, orientations, order alignment, internal axis, molecular long axis, bond directions without necessarily having the full positional order. Solids typically have both the transitional and orientational long range order. Isotropic liquids have a neither liquid crystalline order. Liquid crystals are intermediate phases with the partial order, nematic molecules, long range orientational order, directors and align but no long range positional order. They flow like a liquid symmetric orientation order plus layering the molecules form the 1D density wave layers and may tilt within the layer somatic AC and cholesteric chiral pneumatic locally pneumatic but the director twist is space of forming helical structure characteristic of each. There's a broken symmetry phase underlie the LCD technology, many soft matter phenomena. Quasi-crystal show the long-range orientational order 5-fold, 10-fold, 12-fold rotational symmetry, but no 3D periodic translational lattice. Their diffraction pattern is sharp Bragg peaks indicating the long-range order, but with the forbidden symmetrics. Impossible for the periodic crystal's atomic arrangement described projections higher dimensional periodic lattices by the aperiodic tailings and the Penrose tailings. Now, thus the condensed matter physics is over. Now, last topic is the nuclear particle physics. Nuclear particle physics. No, it was the basic nuclear properties, size, shape, charge distribution, spin, and the parity. Nuclear properties include the size R12 1.2 angstrom, power 1 by 3 farad FM. So shape mostly spherical and deformed for the deformed for the heavy nuclei charge distribution, protons and Fermi level rho are equal to the rho naught and divided by the 1 minus exponential r minus r by the a spin L from the unpaired like nucleons and parity pi equal to the minus 1 key power of the L from the orbital angular momentum, nuclear size, and the charge distribution. Side from the electron scattering or muonic atoms empirical are equal to R and a to the power 1 by 3 RO 1.2 FM charge 1.25 FM matter skin depth equal to the zero point 0.5 FM charge radius r ki power 2 ki power 1 by 2.8 r, and uniform sphere-like nuclei diffuse the 8 for the heavy neutron skin and neutron-rich nuclei. Shape mostly spherical, magic numbers and a prolate oblate deformation beta 2 greater than 0 for the rare Earth heavy and a quadruple Q greater than the 0, and measured by the Coulomb excitation electrons scattering from factors and triaxial pulses in the transition nuclei. Spin and the parity, spin and even nuclei L equal to 0, odd A from unpaired nucleon J cell model, even A non-zero from the collective rotation parity pi plus 1, and for even L minus 1 odd L product for the new multi-nucleon even always pi plus cell model predict the most ground states accurately. Properties and property determinations and the key features. To cite is E minus scattering RA 1 by 3 rho 0.17 nucleons per FM cube. Charge distribution Fermi rho R diffuse skin A zero point 0.5 FM. Shape quadruple Q spherical deform spin L spectroscopy. Now that is a 0, even, odd A parity pi, and the beta decay reactions minus 1 keep our summation of the L. No, the next topic will be the binding energy. Binding energy, semi empirical mass formula, liquid drop model. Nuclear binding energy, energy required disassemble nucleus into the individual protons, neutrons, calculated from the mass defect by the EV equal to delta mc square, picking 8 MeV per nucleon, Fe per Ni Fa or Ni. Semi-empirical mass formula SEMF liquid drop model approximate empirically capturing volume surface Coulomb asymmetry pairing effect binding energy calculation mass defect delta m some bracket 1 ZMP plus A minus ZMN. Now the minus MAZ NPMN hydrogen neutron masses MAZ atomic mass EV 931.494 MeV by the mu delta M mu atomic mass unit binding per nucleon B by A rise liquid to the mid mass nuclei drop heavy fission null viable liquid drop model SEMF liquid drop nucleus incompressible charge drop SEMF BAZ AVA minus ASA2 by 3 minus ACZ minus Z into Z minus 1 divided by A1 by 3 minus A minus 2Z2 by the A plus minus delta AAZ coefficient A 15.5 MeV volume saturation AS 16.8 surface AC zero point 0.72 Coulomb and AA 23.3 asymmetry delta pairing 12 by the A ki power 1 by 2 MeV even fit masses except cells effect and applications limitation explain fusion heavy low B by A fusion light beta stability minimum energy valley and fail near the magic numbers and cell model needed. SEMF terms term physics origins A dependence volume short range N enforce AVA surface low density A minus AS A ki power 2 by 3 Coulomb proton repulsion minus AC Z ki power 2 by the A ki power 1 by 3. Now the next topic will be the nature of the nuclear force form of the nucleon potential, charge independence, and the charge symmetry of the nuclear forces, deuteron problems. Nuclear force is a short range 2 FM charge independent PP NNP forces isospin T equal to 1 triplet charge symmetric PP and N deuteron NPT equal to 0 binding the test saturation biweekly bound the ground state and virtual excited states. Now nature of the nuclear force strong attractive 1 to 2 FM overcome coulombs and repulsive core less than zero point 0.5 FM spin tensor dependent. Saturates no collapse meditated by the meson exchange pions dominant Yukawa potential from the OPEP isospin T equal to 0 deuteron like the tensor strong T equal to 1 strong scattering states. Now the nucleon potential phenomenological read soft core VR, VCR, and V sigma sigma 1 and sigma 2 plus VTS 1 2 and VLS with the central Yukawa Gaussian spin tensor S123 sigma r minus sigma sigma by r square spin orbit realistic argon V18 operators reproduces an scattering phase. Charge independence symmetry charge independence VPP equal to VNN equal to the VNPT equal to 1 rotation. Isospin space SU2 charge symmetry VPP equal to VNN isospin reflection violation MNMP 0.1 P omega mixing EM tested by the PP NP and scattering mirror nuclei delta E. Neutron problem, yes wave bound state BD 2.2224 MeV 4s3 by 296 plus 3d1 AD mixture 4 plus 4% tensor mixes L 02 and asymptotic UR eq power minus KR divided by the R K equal to the root MBD by the H 0.2316 FM minus 1 virtual 1s0 state equal to 1 0 0.068 MeV test charge symmetry magnetic moment mu d 0.857 mu n deviates from the mu p plus mu n due to the d wave properties table. Aspect feature range strength 2 FM 50 MeV. Now charge independent PP equal to NN equal to NPT equal to 1. Symmetry breaking 1% mass EM deuteron loose bound S plus D mix. Next topic will be the evidence of the cell structure, single particle cell model, and its validity, limitation, rotational spectra. Cell structure nuclei evidence by the magical numbers 2, 8, 20, 28, 50, 82, 126 showing extra stability, while the single particle cell model treats the nucleons independently mean field potential succeeding odd A nuclei, failing collective motions, rotational spectra, and reveal the deformed nuclei with the L into the L plus 1 energy spacing. Evidence cell structures, magic numbers, peaks, binding energy per nucleon, neutron, suppression energy, low first excited states, and high isotopes, isotone and stability and low quadruple moments and the high neutron captures cross sections just below the magic n by z electron knockout and the eep by n reaction reveal the single particle energy near doubly magic core like the 10 c 140 ca1 200 pv Now the single particle cell model, nucleons, harmonic oscillator, volt Saxon potential V are equal to the minus V naught divided by the 1 plus exponential R minus R by the A spin orbit VSO magic gas from the large spin orbit splitting P3 by 2 and minus F7 by 2 predicts ground state as J power pi and magnetic moment Smith lines but overestimates the quenching validity and the limitations. Now the excellent and order A near the closed cells and excitation spectra electromagnetic moments of fells from for the even collective vibrations rotations of mid cell pairing the needed and a heavy deformed nuclei collective model needs the configurations mixing pairing BCS rotational spectra deformed deformed nuclei beta is greater than 0 collective rotations ei h की power 2 divided by the 2 l into the l plus 1 rigid rotor moment even ground band 0 plus 2 plus 4 plus with r for 2 3.33 ratio moment inertia from cracking model odd a decoupled bands model comparison model strength limitation cell odd a magic gaps no collectivity collective even rotation even rotation no single particle. Yes, the next topics will be the elementary. Elementary idea alpha, beta, gamma, decay, and their selection rules and fusion, nuclear reactions, mechanism, compound nuclei, and direct reactions. So alpha, beta, gamma, decay, basic radioactive processes constrained by the energy, angular momentum, parity, conservation, while the fusion nuclear reactions involve the rearrangement nucleons through the compound or direct mechanism. The key ideas below match typical BSc, MSc nuclear physics syllabi and focus concept selection rules rather than derivatives. So alpha beta gamma decay. So alpha decay heavy nuclei typically A greater than 150 emit A 4 helium nucleus. A decreases by the 4 and jet by the 2 and driven by the tunneling through the Coulomb barrier and increased binding in the daughter plus alpha beta decay changes jet by the plus minus 1 nearby constant A beta minus 1 n10 to the p plus e minus plus ve beta plus bn plus e plus ve or electron capture moving nuclei towards the valley stability. Gamma decay is the de-excitation of the nucleus by the emission photons after the alpha or the beta decay after the reaction. A and Z stay the same while the nuclear spin parity may change. Now the selections rules for the decay. Alpha decay must conserve angular momentum parity orbital angular momentum L alpha satisfied mod Ji minus Jf less than equal to L less than equal to Ji plus Jf. Overall parity chain pi I equal to pi f minus 1 k power L higher L gives the more hindrance and longer half-lives. Beta decay selection rules follow the weak interactions types. Fermi transition delta J 0, no spin change, no parity change, typical 0 plus, gamma, Taylor delta J 0 plus minus 1 but not 0 plus theta 0 z, 0 plus. So usually no parity change, larger mod J, parity change and gives the forbidden decays longer half caves, gamma decay selection rules come here, multipole radiation for the electric and the magnetic and multipoles. Order L delta J 0 plus minus 1 and plus L with a 0 and not the 0 for dipole. Parity changes pi I pi F minus 1 L for electric and minus 1 L plus 1 for magnetic transition. Higher multipoles are increasingly hindered. Fusion and the fusion. Fusion, a heavy nucleus, often A greater than the 230, splits into two, occasionally three fragments, and the plus now the several neutrons releasing the 200 MeV per event due to the higher binding energy per nucleon. Medium mass fragments, it can be spontaneous or induced by the nuclear neutron capture. Process involves deformation over the fusion barrier, microscopic liquid drop plus cell effects leading to the characteristics mass kinetic energy distribution, delay distribution, gamma rays important for the reactors, weapons, fusion, light nuclei D plus D and D plus D combine to form heavier nuclei with the large Q values 17 to 20 microelectron volt for the DT, but require the overcoming Coulomb repulsion by the high temperature pressure or the quantum tunneling. Stellar energy production is a chain fusion reaction, PP chain CNO cycles, nuclear reactions and the Q values. General reaction A plus A and B plus B conserve nucleon number, charge, energy, momentum, Q value Q, M A and M minus MB bracket 1 C square. Positive exoergic and negative endoergic and reaction cross sections and depend strongly on the energy angular momentum barriers resonance structure compound states measured by the its angular and distributions energy spectra outgoing particles. Now the compound nucleus versus direct reactions. The compound nucleus reactions projectile fully absorbed to form the highly excited intermediate nucleus lives so long enough and 10 to the power minus 16 second lose the memory entrance the channel before decaying statistically by the particle or the gamma emissions evaporations spectra and the nearly isotropic angular distributions are the characteristic. Direct reactions occur on a much shorter time scales with only few nucleons participating typical mechanism elastic inelastic scattering and the stripping pickup DPD and transfer knockout reactions which give strongly forward and peak angular distribution reveal the single particle structures. Now the process main change typical scale features alpha decay A4Z2 tunneling MEV alpha heavy nuclei discrete lines beta decay now the jet plus minus 1 a fixed and continuous electron positron spectra gamma decay excited ground and low level discrete gamma energies multipolarity fission one heavy and two medium nuclei 200 MeV and several neutron fusion two light heavier nucleus no stellar thermonuclear energy and compound reactions formations of the excited nucleus, resonance and evaporation spectra, direct reactions, and a few nucleon rearrangement, fast forward picked products. Now, the next topic will be the classification fundamental forces, elementary particles, and their quantum numbers, charge, spin, parity, isospin, and strangeness, etc. Four fundamental forces govern all the interaction strong, nuclear binding, electromagnetic charge, weak decay, flavor, chain, gravity, masses, elementary particles, standard model classified by the quantum numbers like the charge Q, spin S, parity P, isospin L/L3, strangeness S, baryon number B, lepton number L, color. Force classification. Now the strong force binds quarks into the hadrons and nucleons into the nuclei mediated by the glucons range -1 m, strongest 10 the power 6 times em. Electromagnetic acts on the charged particles by the photons infinite range weak handles and the beta decay and the neutrino interactions by the WZ bosons short range 10 to the power -3 FM parity violating gravity weakest infinite range mediated and hypothetical graviton universal but negligible particle scales. Fermions, quarks, and leptons. Quark spin 1 by 2 p plus and mu u equal to the q 2 by 3 l 1 by 2 l 3 1 by 2 d q minus 1 by 3 l 1 by 2 l 3 minus 1 by 2 CSBT analogous with the S0 minus 1 0 minus 1 0 0 generations 1 S first UD 2 second CS third TB leptons charge E mu tau GQ minus 1 L1 neutrinos mu E mu and mu tau. So Q equal to 0, L equal to 1. All fermions have the B 1 by 3 quarks, beta equal to 0 leptons. Boson, force carriers Higgs. Now the gauge bosons spin one glucons, 8 colors, strong, massless, photon, EM massless, W plus W minus Z naught, weak, massive, 80 to 91 GeV. Higgs boson spin 0, P minus massive, 125 GeV. Give the masses by the symmetry breaking. No isospin strangeness for the bosons. Quantum number tables, particle type example Q, spin P, L, S, notes. So quark mu U plus 2 by 3, 1 by 2 plus 1 by 2, 0, up type. Now the quark D minus 1 by 3, 1 by 2 plus 1 by 2, 0, down type. Lepton E minus -1, 1 by 2, minus 0, 0, charge L equal to 1, gauge boson, gamma photon, 0, 1, -1, 0, 0, massless EM, Higgs H 0, 0, minus 0, 0, mass generations. Now the next topic will be kya? Gell-Mann-Nishijima formula, quark model, baryons, mesons, CPT, invariance, application, symmetry, arguments, particle reaction. Gell-Mann-Nishijima formula relates charge Q equal to the I3 plus Y divided by 2 hypercharge Y equal to the B plus C B plus S C plus B dash T to isospin and strangeness, enabling SU3 flavor classification. Quark model builds hadrons from the UUD type, baryons, QQ, mesons, symmetry dictating multiplet CPT invariances, test discrete symmetries, decay reactions, violated weak force but conserved overall CPT theorem. Gell-Mann, Nishijima formula. Charge formula Q equal to I3 plus B plus S divided by the two originally extended charm C isospin I3 level SU2 doublets UD plus 1 by 2 minus 1 by 2 hypercharge Y follow Y for flavor SU3 example proton UUD I3 plus 1 by 2 B equal to the 1, S equal to 0, Q equal to the 1, summation minus ADDS, I3 equal to the minus 1, Y equal to the 0, Q equal to the minus 1, predicts particle charge in octets and decuplets, quark model, baryons, mesons. Baryons will be the QQQ be equal to the 1 spin 1 by 2, 3 by 2, nucleon octet, P and summation angular for all and decouplet del decouplet spin 3 by 2 mesons and q bar and b equal to 0 pion triplet pi plus pi 0 pi minus rho kaons neta eta and wave function antisymmetric color singlet spin flavor su6 combines spin isospin magnetic moments and quark additivity cpt invariance change charge conjunction C particle antiparticle E plus E minus gamma gamma conserved and parity P mirror reflections R vector minus R vector violated weak decay W U dash S and 60 CO beta theta tau puzzle time reversal T V vector minus V vector K naught decay. So violation CPT theorem holds particle antiparticle equality weak and neither C nor P conserved, but the VA preserves maximal and CPT violated indirectly. Symmetry applications in the reaction conservations law select allowed channels strong interactions conserve LSPC delta L 0 plus minus 1 number delta S equal to 1 electromagnetic conserves PCL within the multiplates Wick equal to the Wick delta S equal to the plus minus 1 by 2 rule Cabebo delta L 1 by 2 K equal to 2 pi versus 3 pi isobar model delta 1232 N pi P even L 3 by 2 forbidden decays 0 plus gamma from angular momentum parity. Now particle classification category. Now the examples quantum number key and symmetry group. Now the baryon octet B and summation and angle overall. Now the B equal to 1 L 1 by 2 minus 1 S 0 minus 1 SU 3F baryon decouplet del and summation star omega B equal to 1 L equal to 0 minus 3 by 2 S minus 3 SU 3F meson nonet. And now the pi k neta b equal to 0 L equal to 0 minus 1 S 0 or plus minus 1 SU3 F lepton E V E mu L equal to 1 Q minus 1 0 S 0 non singlet. This is last topic of the nuclear physics, nuclear and the particle physics. Parity, non-conservation. What topic is the parity, non-conservation in the weak interactions and relativistic kinematics. Parity, non-conservation, weak interaction confirmed by the WU experiment and 60 cobalt and beta decay show electrons prefer emission opposite nuclear spin distinguishing left from the right relativistic kinematic particle reactions uses the four momenta conservations Lorentz invariant Mandelstam variable STU. Parity violation of weak interactions of weak forces selects a parity P invariance V a current structure and a left-handed fermions only predicts asymmetric and the beta spectra WU experiment in 1956 polarized the 60 cobalt and J equal to 5 plus at the low T show the E minus emitted anti-parallel to the spin non-symmetric and if the p conserved resolving theta tau and puzzle k plus 2 pi to 2 pi versus 3 pi and subsequent v scattering neutron decay symmetry and equal to the minus beta is a 0.99 measured and strong em and conserve the B, and a weak maximal violation, no right hand current at the low energy. Key experiments implications: W beta decay electron and upper down spin direction is symmetric. Garvin's Lederman telegiddy mu plus decay positrons asymmetric spin rest frame. Neutron P and the um, implies neutron left hand V mu L, antineutron right hand VR VA Lagrangian, and zeta gamma kipor mu 1 minus gamma 5 and zeta CP violation letter KL pi pi. So, but the P alone broken. Now, relativistic kinematic basics. For momentum, P ki power mu and equal to E by C, and invariant mass m square c square e square by c square minus p square. Two body reactions A plus B C plus D S equal to the PA plus PB की power 2 CMS energy square T equal to PA minus CPC square momentum transfer U equal to the PA minus PD की power 2 S plus T plus U equal to summation I m I की power 2 C4 threshold equal to the root S greater than equal to the mc plus mc plus md bracket 1 c square. Left frame is the projectile energy e lev relates to the root s equal to the root 2 root s equal to the root 2 m a e lev m a target kinematic formulas. Center mass total now the equal to 0, and the p fractions now the square root now scattering angle theta cos, and for the Jacobian phase space d phi more proportional to mod p d phi 2 pi h cube 3. So application table dk 1 to the 2, now the e1 and fraction m ki power 2 m ki power 1 and minus m2 ki power 2 2 mc ki power 2. So elastic scattering t equal to the minus 2 p ki power 2 1 minus cos theta threshold productions root s greater than equal to summation mc square invariant mass m and 1 to ki power 2 c ki power 4 p1 plus p2 ki power 2. So that's all, and all the best for the exam.